You know, the main thing on a battery bank that you need to maintain is that when the battery is in use, it causes water to evaporate out of the battery. And so there are plenty of watering systems, some which can even be automated and water your batteries automatically. But really, watering your battery is no big deal. In fact, it's less than a 2-minute process. It's literally you're just taking a watering tank and then just connecting it up to a nozzle that then goes and fills all the batteries in your bank. Uh, then there's a variety of watering systems available. Normally, you get just whatever's recommended by the battery manufacturer. What is a little bit more tedious about maintenance is not watering the battery, but measuring the battery specific gravity, which occurs at the same time that you're watering the batteries. So the reason why you have to monitor the specific gravity of the batteries for warranty compliance, which is obviously something you're going to want to do with a battery bank that is this expensive. And that's where the maintenance kind of starts to get a little bit complicated, because the cheap products for monitoring the specific gravity, in my experience, require you to take, you get these holes in the top of the battery, and these are where the watering caps from the previous slide would fit into. And so then to stick your hydrometer down into the battery, because of the size of the tube, you got to take the watering cap out of the battery, then stick the hydrometer back in, and then take your measurement and then put the watering cap back in. So that's what takes the most amount of time when watering the batteries. There's more industrial tools that can monitor the specific gravity digitally, that can fit through battery watering systems, but they're much more expensive. We're talking about $1,000 versus $20, and so most customers, that's they're not going to want to shell out the money for that digital tool. I think that actually is an opportunity here, where you look at, say, the cost of a grid connection of being $25 or $30 a month, where if you get enough off-grid customers in a given region, maybe instead of paying the utility for that metered connection, you pay a solar company an equivalent amount to come by and maintain your battery. Now, the battery manual says the hydrometer readings need to occur weekly for maintenance. There's actually a little bit more wiggle room in that. You water your batteries and you maintain your batteries when you're using them. And so in that winter period where you're really operating your batteries all the way down to their low end range because of lack of sunlight, that's when this becomes a weekly task. Or maybe in the summertime, with your high air conditioning loads, you're cycling your battery more deeply, it's evaporating more water, and that's when this becomes a weekly task. In the spring and in the fall, when your batteries are not being cycled so heavily, this might spread out to every 2 weeks or every 3 weeks rather than weekly. But taking those voltage logs is the tedious, kind of time-consuming part. So we're talking about like a 15-minute maintenance that at its peak, during peak season, is a once-a-week task. And so some customers say, well, I don't want to deal with that. I'd rather go with a maintenance-free battery. And at that point, you just end up spending 40% more on your battery bank for a sealed battery that's not going to last as long. So my personal taste is to go with the sealed battery and then or go with the unsealed battery, and then if the customer doesn't want to perform the maintenance, offer them some kind of discounted maintenance plan. Just with project planning, if you're going with industrial flooded lead acid, check the weights of the battery. That can become kind of a project logistical issue, because if they ship out in a standard pallet, that pallet's going to end up weighing over 3,000 pounds. And a lot of your low-end machinery for moving stuff around may only have a weight limit that, a hoist may be able to pick up one battery at a time if it has a 2,000-pound rating. The lift gate or your Bobcat may only be able to pick up 1 or 2,000 pounds. And so you might want to end up spending more money in shipping and get the batteries shipped on multiple pallets rather than on one pallet, or have a strategy for breaking out the pallet in the truck before it coming down the lift gate so you can actually get it out of the truck without renting more expensive equipment. Lithium ion does represent a competitive threat to lead acid batteries. In my opinion, it needs to drop by about 50% in price to really overtake the value of industrial flooded lead acid for off-grid purpose. And that should occur over the next few years. So if you're not getting into your off-grid project for 5 years from now, it very well could be that a maintenance-free lithium-ion battery is the way to go. And that lends the concept of a starter battery where you may only design your first battery bank to last 5 or 6 years. You may run the heck out of it and deep cycle it all the way down into its damaged low end range and say, okay, I'm not going to do the 120 or 90 kilowatt hour battery at this moment in time. I'm going to do something smaller, something that's going to last less long, and then swap out for the latest and greatest battery in a few years from now. Of course, with my customers, they're not really interested in revisiting the battery installation, just 5 or 6 years into project ownership. And then the other aspect is, these lead acid batteries, when you oversize them, and so we see that your battery is going to be fundamentally oversized because most of the time you're cycling it maybe at 20 or 30% only on stormy weather systems. When they pass through, do you get down into that 80% cycle that they could last a very long time into the aspect of decades rather than just 5 or 6 years. Lithium ion may very well be better for grid tied applications. With a lithium ion battery where you're cycling it every single day, when you're cycling it in under 2 hours with a small battery, it's more elastic. But it's hard to have just the raw storage capacity that you need to run a full-sized house off grid. It's hard just to come up with a budget for lithium ion at this point in time. And so the raw storage capacity becomes a problem with maintenance-free batteries because you run out of budget. All right, so let's talk about inverter selection. One thing that kind of jumps out at me with off-grid is you don't have the same level of review that you get with a grid-connected system. And so in my neck of the woods, sometimes it can take a couple of weeks. And in fact, the template says it could take more than 30 days between the time you drop off your solar permit and then you get permission to proceed. Whereas with off-grid, you don't have an interconnected solar array. You don't have to deal with the grid authority. You still may need to have a building permit or an electrical permit, depending on your jurisdiction, but you may be able to avoid the process of dealing with the utility and all their extra rules and regulations for a grid-tied system. So a good example of that would be many utilities require an external disconnect switch for a solar array. It's not part of National Electric Code. Often you'll get disconnect switches either built into the inverter or, technically speaking, the switch on your electric service panel could be a disconnect switch for your system, but they may require an additional knife switch. So what that means is there may be some functionality on a battery inverter, such as many battery inverters have a transfer switch built right into them that can switch you off of grid power and then onto your battery bank or onto your solar power. And you may not be able to use that full functionality because the grid comes in and says, well, we don't want you to use the internal switch that's inside the piece of equipment because we would have to take the equipment apart to be able to visually inspect the switch and be assured that there is a full, manual disconnect. It's to the point where some utilities require viewing windows, a little transparent window to be ordered into the disconnect switch so they can actually see inside of it. And when you turn the switch off, they can actually see the blades disconnecting. And so you end up starting to not being able to use the full battery inverter functionality or see increased balance of system material. And it's nice when you go off grid to not really have to worry about that. What that also means is you might find some off-grid battery inverters that are not rated for grid connection, but that are still perfectly suitable to your needs. So often the grid-connected inverters, they put in more stuff inside the inverter to improve the efficiency, go for a 97 or 98% efficiency. You might be able to find an off-grid inverter not rated for grid connection that might only have a 90% efficiency, but it might end up costing thousands of dollars of less than the grid-connected inverter. So that's one strategy we use in our off-grid designs is we say, okay, well, I can take a grid-tied battery inverter and to get 12 kilowatts of capacity out of it, I need to double stack it. And because I need to double stack it, then I need to buy a service panel so I can wire these inverters into parallel with each other. And that's usually a specialty panel for a couple of reasons. So you end up buying, not only to get the output power that you need to run your house, you end up buying multiple expensive inverters and then a whole bunch of expensive balance of system material just so that you can interconnect to the grid with that UL grid connected approval and with the approval of your local jurisdiction. Whereas you might be able to save a few $1,000s by going into off-grid product lines that the solar industry would consider to be lower end. Because they're at that lower efficiency rating, they're not rated for grid connection. There might be a bias from the solar installer to say, oh, well, that's a cheap battery inverter, so that's not going to work with you, when the reality might be that the cheap battery inverter that's not rated for grid connection can do everything that you need to power your home. They just haven't incurred the cost of going through the UL listing process. And they also, you may be able to use some of the more features that are built into it. So a good case in point would be, I'm a big fan of an inverter company called AIMS, AIMS, mainly because they're cheap and they do a 12 kilowatt battery inverter that can power a mid-sized home. But the AIMS inverter is not capable of double stacking. So if you wanted 24 kilowatts of power instead of 12, you couldn't use the AIMS inverter. But the AIMS inverter has a transfer switch, all this stuff, built right into the inverter. So, for the right system, you don't necessarily need the high-end battery inverters that are more common with grid connections, such as Schneider or Outback or SMA or Magnum. So just doing a little bit of a comparison, um, let's say you got, two Schneider inverters, and they cost about $3,000 a piece, and then you bought the specialty distribution panel, and then you went and bought, this is actually not completely everything you need. You still need to go and buy the charge controllers, compared to, in Ames inverter, which I need to update this pricing. I think what I did on on apples to apples comparison is I put the two charge controllers necessary into this system, but not this one. And the Ames inverter itself is $3,000, not $5,000. So, what when I made this slide, I need to, this also includes the charge controllers. And so the Ames inverter is not UL listed. It does have a listing with ETL, but a lot of jurisdictions in the US, they want to see that UL listing. They want to see, external disconnect switches that can go up and down. That's kind of the up indicating on, down indicating off, which you don't get if you just land your inverter on the panel directly. So the fact of the matter is, you end up spending maybe $3,000 to $4,000 more to get a multifunctional battery inverter that is rated for grid output, that has a variety of modes of operation for commercial and residential. You don't just need to use these grid-tied battery inverters for living off grid, or reducing your electric bill. They have advanced settings. Sometimes they're used to just smooth out the variability in a generator. Sometimes they're used to do demand management for the building, and just they turn the batteries on to limit the current coming into a building. A lot of modes of operations that you just won't use from that battery inverter, and yet it has all the development cost and material costs to deliver that functionality that you'll never use. So you end up overspending on a battery inverter system, whereas with off-grid, you might just get a battery inverter that is actually made for whole house off-grid operation, that comes in a cheaper shell. Then again, one problem with just buying a single battery inverter, even if it's a higher capacity, so one 12 kilowatt inverter instead of two 6 kilowatt inverters, is that if that inverter goes down, your whole system goes down. Whereas a more expensive system features some double redundancy, where if one inverter goes down, the other inverter can remain online. And so on my very first off-grid system, we went with, higher end, more expensive products in order to make sure that if there were any mistakes made in the design, we could add additional inverters to get more power, that there was some double redundancy, so that if something happened to one inverter, the good doctor's house would not run out of electricity, that they could limp along with a smaller system until the service call was made. But that does increase your project budget. And when you look at the, let's say going with a higher end battery inverter system versus a lower end battery inverter system, has a hard cost of $2,000. And then you're looking at, let's say you're in a anti-solar jurisdiction, which is going to charge you a higher monthly fee because you're a solar customer, and maybe in that same jurisdiction they don't give you any sort of net metering, and so you're only selling back at 2 or 3 cents anyway. You look at all of these smaller costs, and it says, okay, well, if I have to spend $2,000 more on an upgraded inverter system, and then I have to spend, as we saw in the example yesterday, about $8,000 to just make up for the revenue of my bill being increased, and also selling back to the grid at avoided cost rather than at at full retail value, it starts to say, well, why don't I just start chunking that money into a battery bank instead? And so, as solar, if you're in an area where the utility does not have good solar policy, that gives the customer more motivation to say, well, I know battery-less solar costs a lot less than battery solar, but it doesn't give me everything I need. Why don't I just go off grid? And if it's going to be more expensive to keep my grid connection than to go 100% off grid, then I'll just go 100% off grid. And given in mind with industrial flooded lead acid costing substantially less than lithium ion, that all of that additional cost to be grid connected could just go directly into your battery bank. Then the other aspect is the development schedule. You look at an off-grid array where basically you can just call the power company and say, all right, come and pull the meter because we're no longer your customer, versus submitting to them the design, the permit, the reviews, any additional fees they want for reviewing your application permit. It's a nicer construction schedule as well. There are minimum amount of okay, we have a good question from Mark. How noisy are the inverters? Is there a big difference between high-end inverters and low-end inverters in terms of noise? And the answer is yeah, your battery inverters are noisy. And mainly it has to do with if they have a transformer or not. And most battery inverters are going to be transformer-based. I can't really explain the nuances between transformerless and transformer, except that often you'll have a transformer and an inverter that is intended to go into multiple regions of the world. So they just have one output, and then they sell you an additional transformer to give you that. One common reason why you would have a transformer is that your solar inverters may be outputting 240 volts, but they're not outputting 120, 240 split phase. And so they'll need an additional transformer to give you not just 240 volt output, but also 120 volt output. It's the transformers that make a lot of noise. So, that is something that, like, even on the Schneider battery inverter, which I would consider to be a higher end battery inverter, it's noisy as all can be. This is not an inverter. With a lot of solar inverters, you just put them on the side of your house, hang them on outside, and then wire them up to your service panel or utility meter, but they don't have that transformer inside them. With a battery inverter, you really want to put it in an enclosed housing and then insulate the housing for noise. So what we're looking at in our designs, in the upcoming designs, is actually building a dedicated box outside of the house that has an air conditioning unit in it, a small air conditioning unit, like a portable air conditioning unit with a heating element and the inverter and the batteries all enclosed in a SIP panel, insulated box for noise reduction. If you put your battery inverter inside your garage, you're going to hear it. It would be better to put it in an enclosed room inside of your garage. It's not something you just want to put outside next to your doors because you're going to hear it 24/7, ruining the ambiance of your off-grid house. So yeah, the battery inverters are much noisier than your transformerless solar inverters. The solar inverters can still go outside. Let's see. What I wanted to point out on here is there is a minimum battery size that you need to install on your inverter. So usually it's very easy to meet, and you're going to want to do something larger than that. But we look at this Schneider inverter in its documents. It says our minimum battery bank size is 440 amp hours, and that's about 20 kilowatt hours on a 48-volt battery bank, or 10 kilowatt hours on a 24-volt battery bank. Of course, if you get into those small battery sizes with lead acid, the problem is if you go for the very bare minimum, like a 20 kilowatt hour bank or a 10 kilowatt hour bank, and then you go and you use the full rated capacity of the output of the inverter, you could use that full rated capacity during the day. Because if you have more than 7 kilowatts of DC power going through outputted and your batteries are fully charged, you could be drawing 7 kilowatts through that inverter without discharging your batteries. But then at night, if you use the same 7 kilowatts of power coming out of a very small battery bank, then you get into that below C5. You get into that rate where you could 7 kilowatts on 20 kilowatt hours, that's a C3 charge. 10 kilowatt hours on 7 kilowatts, that's a C1.5. And most of that electricity is just going to be burned up as heat. The point is, in that kind of system, you would have to really limit your loads to make sure you're not, you can use the full inverter capacity during the day, but not at night unless you increase the size of your battery bank. You could, if you had a lithium ion battery bank like the Tesla Powerwall, use that full 10 kilowatt hours within a 2-hour time frame at night. But then the downside would be, if you're off grid, you would then be out of electricity until the sun comes back up. There's a debate in battery-based inverter design on DC versus AC coupling. And the difference is, with DC coupling, you wire the modules directly to the batteries. And so you put a voltage regulator, which is also called a charge controller, between the array and the batteries. And usually with a solar array, the voltage is going to vary and jump up and down, and the amperage is going to remain relatively constant. And so a voltage regulator turns that on end. The batteries really want to see a constant voltage and have the amperage fluctuate, whereas the solar modules raw have the varying voltage with the amperage remaining relatively stable. What the charge controller does is it regulates the voltage, and it'll vary the amperage. And so, going with PV modules, generally you're going to be operating at around 400 or 500 volts. You also have the issue of your battery bank being a 48-volt system, so you have to step down that voltage. The question is, well, how do you step it down? You step it down by installing a charge controller between the array and the batteries, or do you just keep the solar array on their own inverter like normal, and then have a standalone inverter for the batteries? And so, you have the modules going from 400 or 500 volts DC into 240 volts AC. The output of the battery inverter is 240 volts AC, and it sucks power up to charge the batteries, versus DC, where you just kind of go into the batteries first before hitting your service panel. And in terms of which is better, well, you're processing the electricity once, stepping it from 500 volts to 240 volts, and then you're processing it again to go from 240 volts down to 48 volts, and then you're processing it again to go from 48 volts back up to 120, 240 split phase, and then you go into your load. So we would call that a 1, 2, 3 step process. Whereas if you share the inverter and put a charge controller between the modules and the battery bank, to get to your load from your batteries, the power goes from your array. That's a 1-step process. And then from the batteries out through the battery inverter, that's a 2-step process. So technically speaking, DC coupling should be the more efficient way to go about it. Furthermore, in a charge controller is just a flat DC to DC transformation from a high voltage down to a low voltage, whereas an inverter is not just doing DC voltage regulation, it's also doing DC to AC transformation. And so technically speaking, having two inverters versus an inverter and a charge controller, the two inverter process should be more expensive. And so for off-grid living, a DC coupled system should be cheaper and it should be more efficient. I would say the issue with that is there's simply more solar inverters being manufactured than large DC charge controllers. And so the DC charge controllers for solar going into a battery don't have the same economies of scale that the plain old batteryless inverter manufacturers have. And so even though technically speaking, the DC charge controller should be cheaper, the prices are pretty similar. I mean, we're talking about for a DC charge controller, a good budget is around 20 to 25 cents per watt. And then, your low end batteryless inverters are already at that price point. And then sometimes on the higher end inverters, you get into maybe a 30 cent per watt price point. And so I would say because the market for the last 10 years has been focused on batteryless systems, the price difference between battery components and batteryless components, even though the battery components might have technical reasons to be cheaper, the real price difference isn't there. AC coupling is also very popular when you do have that, these are power lines, when you do have that grid connection, because on an AC coupled system, the battery may just hang out and not do anything until there's a power outage. And so you don't incur that 1, 2, 3 step process. You just kind of direct drive your load with solar, and any surplus goes out onto the grid. That would be a one-step process. So AC coupling has some real advantages even when you have batteries if you're grid tied, and that means the whole grid tied and also batteryless market kind of rewards the AC coupled architecture. Although if you're starting from scratch, there is one real advantage that an off-grid DC coupled system provides. So the problem is, let's say your home goes overnight and for whatever reason you don't manage your batteries and you fully drain your batteries. So now your batteries are fully drained and your house runs out of power, and that stinks. And you say, okay, well, I'm just going to wait for the sun to come back on. And so the sun comes back up and it turns on your solar modules. Well, AC coupled solar inverters, they need to see a grid signal to turn on. And so you could have an AC coupled off-grid system where if for whatever reason you fully drain your battery bank, the sun comes back up, but your solar inverter doesn't turn on, and then you have all this power that your house can't use. Whereas if you fully drain your battery banks under a DC coupled system, that charge controller will power up from the DC array power and charge your batteries. And now that your batteries are at a full level, your battery inverter will turn on and function. So there is a little bit more security in a DC coupled system. But even that is not particularly important because, often what will happen is that either you'll program your battery bank so that it doesn't fully drain, so that there's a little bit a tiny bit of reserve capacity left in it so that in the morning it can wake up the solar inverter and then recharge itself. Or what's even more common is you have your generator as part of the system too. And so if your batteries fully deplete, the generator will turn on, and not only can that turn your solar array back on under the right configuration, but it can also charge your batteries back up. And so the debate between DC coupling and AC coupling should almost be pushed back into academia, because it's really just a question of, well, what's your starting point? A lot of customers, they already have their batteryless solar array on a batteryless inverter. And so if you wanted to convert them to go 100% off grid, all you would really need to do is AC couple a battery bank, and there you go. You don't have to do any rework. You don't have any sunk cost in your that you aren't able to use because you have to toss out your batteryless inverter. No, you just go with a battery inverter, and then you don't buy the charge controller, and you're off to the races. That said, when I'm doing my systems, starting completely from scratch, I prefer DC coupling just because it does provide that extra level of security. And also, unlike a grid connected home where the battery is just kind of hanging out, not doing anything until there's a power outage, on an off grid home, your batteries are being used for the vast majority of the day. Your solar array may be on for 8 to 10 hours, but that is a third of the day. So you're using your batteries much more. And so that's where that two-step process comes back into play, to say that the DC coupled systems are slightly more efficient than the AC coupled system. So all else being equal, I like DC coupling for off grid, but if it's a retrofit, if I'm retrofitting an existing solar array and adding batteries to it and taking the home off grid, there's absolutely no reason that you can't just use what you already have on site and go with AC coupling. And of course, you could always add another solar panel or two on a smaller charge controller, almost like how a generator, like a whole house generator that has a push button start or an automatic start, inside that generator is a battery for the generator so that the generator can start. And it's not a battery that you could run your whole house with. It's just there for the generator. You might have a DC coupled solar module on the battery bank itself that's just to make sure you have a way to charge up the batteries if the rest of the system, for whatever reason, is offline. So you're not really ever going to be pigeonholed into one or the other. As a very loose rule of thumb, I would say AC coupling is the preferred architecture for grid-connected systems, and DC coupling is the preferred architecture for DC coupled for off-grid systems. But the cost advantages of going with DC coupling really aren't there today, because batteryless inverters are so cheap today, whereas DC charge controllers are still in kind of their infancy. When I got into the solar industry, your batteryless inverters were 40 to 50 cents per watt. And so a 22 or 25 cent per watt charge controller would have absolutely have been the cost-effective way to go. Well, nowadays your batteryless inverters are 20 to 30 cents a watt, just slightly more expensive than your DC charge controller. And so it also comes into a siting issue where, if all of your electronics are in the same location, that's a good opportunity for DC coupling. But if you're building a microgrid where your solar array is being interconnected at a completely different point on the facility than where your battery inverter is going to be located, for reasons such as temperature, just the raw space, noise, At that point, if your solar array is far apart from where your battery bank location is going to be, that would be a reason to go with the AC coupled system, even if you're starting completely from scratch. And you can always, in that AC coupling system, use a generator, as we've discussed. So there's a wide variety of charge controllers on the market. Um, you can buy a $15 charge controller for just one solar panel that'll power up a USB outlet and be connected to a 12-volt battery and, one solar panel. So there's if you're a hobbyist, you can find a nice little $15 charge controller that's, another popular charge controller, and they don't call it a charge controller, but is in the SolarEdge DC optimizer system, where up on your rooftop you put a voltage regulator, and it behind every single solar module. So most solar modules are outputting 30 volts and about 8 amps. Maybe nowadays it's more like 40 volts and 8 amps. Well, what a DC optimizer does is it'll step that voltage up to 380 or volts or so, and for the circuit, and regulate the voltage right up on the rooftop. And that's in the SolarEdge platform. They're kind of the DC optimizer guys. And so you may already have kind of the same functionality of a charge controller in terms of the SolarEdge system regulates the voltage back to the inverter. So instead of the inverter getting varying voltage on the SolarEdge system, the inverter gets a constant voltage. We have to remember that these charge controllers are coming out of an era that predates the batteryless solar industry, but it's also been an application for very small systems, whether it be a small cabin or a weather monitoring station or what have you. The history of the charge controller is one where solar modules were very expensive, and if you were doing an off-grid system, you would, because of how expensive the solar modules were, you would want high efficiency, and you would only be able to afford a few solar panels. Nowadays, it's kind of the opposite. Solar is cheap, and you can just design around your power usage by, overloading on the DC side. And the danger of that is a lot of the charge controllers that are on the market today are still based around, the smaller off-grid architecture of years past. And so here's a charge controller that's only designed for 150 volts of input. And a solar panel outputs about 40 volts. And National Electric Code requires you to oversize that by about over 50%. And so you're looking at each solar panel, let's just make the math simple, is about 60 volts. And what that means is you may only be able to fit 2 or 3 solar panels onto one charge controller if it's a 150 volt charge controller. And a lot of the leading brands of charge controllers have lagged far behind in terms of getting up to a 600 volt architecture. And so your batteryless inverters are on 600 volt architectures. And so when I do batteryless solar design, I'm used to having not 3 modules, but 8, 9, 10, 11 modules on a given circuit. And now with the off-grid system, I have to come back and do 3 modules on a given circuit. And so I was designing this off-grid home, and we had 22 kilowatts of solar on the rooftop. That's about 75 solar modules on the rooftop. And it was like, are you kidding me? Am I going to have dozens of circuits to wire up on a roof? That labor aside, it's going to be a tangled mess of wires if I have 30 different solar circuits up on my rooftop. Now, if you're on the ground, if you're doing a ground mount, having 3 module circuits, I guess was just something that was just natural back when the arrays were small, and it really wouldn't be a huge pain, even on a larger array on a ground mount. But there is something that's just nice about longer solar circuits in terms of labor savings and less complication. And so when I did a review of all the solar charge controllers on the market, I only found 2 that were a true 600-volt charge controller. And ironically, what I would say is the most popular battery system in the US market, which is Outback. And Outback is not so far apart from Magnum and Schneider. They all kind of owe their roots to a company called Trace. And so these inverters are more similar, or these charge controllers are more similar than different. And then SMA uses Midnight, and you can just kind of see the physical similarities Outback has gone to kind of mimic the Midnight charge controller. Midnight has a very strong quality reputation, but like Midnight's charge controller is 150 volts. And so I'm not going to use that on the rooftop because the circuits are going to be too small. Outback, I think recently they've gone up to 300 volts, but that's still half the voltage of a true 600 volt charge controller. And so right now it's odd, but there's really only 2 true 600 volt charge controllers on the market. There's a company called Morningstar and then a company called Schneider. We ended up going with Schneider for our system because Schneider has such big brand name recognition. Whereas Morningstar is a good quality reputation as well. But I was and in fact, you can kind of look at it where the Schneider is kind of the generic, whereas with Morningstar, they're like, oh, heat vents. So our charge controller is going to dissipate heat better than that Schneider. And that alone might say, well, the Morningstar inverter is a little bit better than the Schneider inverter. Nah, we want the Schneider. We're in Mississippi. We don't get good solar distribution. We're going to go with a company that's actually doing more than just solar in our area. So that's, the main takeaway from this slide is that you have to be careful with your charge controller selections, particularly if you're in the solar industry, because you might find that, now I'm using my GoToMeeting drawing tools. It's getting a compliment. How did I get that? Hold on one second. I'm trying to figure out. Let's see. Where's my? Here we go. You just might find that you're dealing. It might surprise you that not all the charge controllers go up to 600 volts like they do in the batteryless inverter industry. In fact, one kind of advanced configuration I'm looking at for some of my designs now is you can buy 1500 volt modules, and National Electric Code says you can only do 600 volts on residential buildings. But I have one design that's upcoming where the ground mount is going to be very far away from the home, and it's right next to a fence, and it's very easy to kind of build an extension of the fence around the solar array. And so what we're actually doing is going into the utility scale sector and finding basically it's the DC optimizer for the utility scale, and that'll give me a 1500 volt to 600 volt output. And so we're going from 1500 volts with the solar array down to a 600 volt home run, and then landing on a 600 volt charge controller, and that's resulting in the most cost effective system architecture for reasons that we'll get into in a few slides. Now, on the flip side, where going with the higher voltage, higher amperage, larger battery products comes back to haunt you is that they're just not manufactured in very sufficient quantities. So each of these charge controllers lands on a DC breaker, but when you think about it, okay, so this is a 600-volt input, and one circuit of modules is about 8 amps, and lo and behold, this is a 4.8 kilowatt charge controller. It can fit almost one pallet of solar modules on it, not quite. Okay, well now it's coming out on a 48-volt battery bank, and so the breaker is sized for 100 amps. And just what DC appliance in your house would land on a 100 amp breaker, on a 100 amp DC breaker? Well, you don't have one. They don't really exist. Maybe some medical equipment, maybe some kind of water pump, but it's not a common item. And so you go and you buy your charge controller, and then Schneider says, okay, well, you also need to buy the breaker, and the breaker costs $100. It's like, oh, well, I'm trying to spend my money on batteries. I'm not trying to spend my money on breakers. And so on one of my designs, we needed to upgrade our breakers. I made a design error. This is rated for an 80 amp output, and my design error was that I ordered the 80 amp breaker rather than the slightly oversized 100 amp breaker. And we were getting into spring, and our array was at full power. And whenever the home would draw the full rated power out of the inverter, the charge controller was delivering its full rated power to the system so that we wouldn't have to use the batteries. And so that meant we got up to the 80 amp output, and the breaker kept tripping. So I was like, okay, well, I actually need to fix my design mistake. I need to go and get the 100 amp breaker instead of the 80 amp breaker. Well, we had 3 of these charge controllers, and that was going to be a $300 in just material cost error. And I was like, I don't want to spend $300 on just a breaker swap out. And so I looked at the OEM on this breaker, and I was able to find a part online for a different piece of equipment that was actually 6 100 amp breakers, and they were ganged together in groups of 3, but it was the same breaker, and these are single pole isolated breakers. I was able to find 6 of them for $50 instead of 1 of them for $100. And so it's not that these high amperage breakers aren't out there. It's just that they're not widely distributed. And, unless you've already bought one, you're not going to know the OEM to go in and find what you need. And so that breaker cost became a little bit of an annoyance. And just from having a little bit more experience now, I know that I don't have to buy these breakers from the manufacturer, that I can go find them in other applications and order them there because they're otherwise the same. But that's another thing to look out for, is the breaker costs. Let's see. I want to show you. This is a manufacturer called Pike. And Pike has been around for a couple of years now. They're a battery inverter startup located in Portland, Maine. And it's like, well, how on earth are they going to make it? Because there's already an overcrowded inverter market space, and with heavy hitting competitors. So where is there room in this market for a battery startup? But what they were focused on is saying, look, we're going to make products that are optimal for solar as it is in today's market. And so it's very similar to the Solar Edge system, where they have an inverter that's being fed a constant voltage. And so they say, well, we already have this constant voltage coming out, and your modules are operating at around 400 to 500 volts on a normal day. And so they put a charge controller not behind every single module like SolarEdge does, but they just put one for the entire circuit. And so their voltage regulator is a little bit cheaper than the SolarEdge system. And that provides a constant voltage with fewer parts going back to the inverter. And then they tap on onto this DC bus a higher voltage battery bank. And as far as efficiency goes, it's a very efficient system, as is the SolarEdge battery. And the reason is because you're going from like 400 volts of solar down to a 380 volt battery down to a AC 240 volt output. And so the closer these voltage ranges are to each other, the more efficient that energy conversion is going to be. You know, you compare it to a solar array where you're going from maybe 400 volts down to 48 volts and then back up again to 240 volts. You know, that's the real reason why your lower end battery inverters that are based around like 48 volt battery banks are so much less efficient than your kind of lithium ion technology battery inverters, because the lithium ion batteries are all based around this higher 380 volt platform. You know, the main problem with a 380 volt platform is that lithium ion batteries are expensive, and there's only one 380 volt lead acid battery on the market that I know of. And they've kind of partnered with Pike, and it's not a unsealed battery, it's an AGM battery. And my preference is, if I'm buying an AGM battery, I'd rather just buy a lithium ion. You know, really what you want to do is if you want a lithium ion battery because of its elasticity and more rapid discharging, what you really want to do is combine them. And even Pike, which has one of the more advanced battery management systems on the market, they have a lead acid option, they have a lithium ion option, but they don't let you combine the two. That's what the last part of the program is going to be about, is it possible to combine all this stuff together? So we're going to come back to inverter design discussion, but you know, we have to keep going a little bit. So we'll get back to that at the tail end of the program. Let's talk through some control room layout issues when you're designing your battery room. Some stuff you need to be aware of. Just a common kind of design error is that electrical equipment needs to have dedicated space and dedicated working space. And what that means is it can't share its space with water lines, gas lines, even air conditioning ducts. Code requires electrical equipment to have its own space. Now that space can be right next to, and so generally speaking, from the floor up, you need about 6 feet of room, and then you can have your air conditioning duct. Or, you know, the space line can be right at the side of your equipment. As long as you have enough clearance to work on that side, then you can have your gas line on the other. But what you can't have is, say, like a gas line running underneath where the service panel should be, because that would be a space violation. So, you know, you really need dedicated working area around your electric equipment. Ventilation. Hydrogen gas is like 5 times more explosive than gasoline vapors. So a very small amount of hydrogen gas, which is what flooded lead acid batteries emit, is explosive. Now, hydrogen, number one on the periodic table, it's a very lightweight gas. So what it's going to do is it's going to float upwards. And so it's not too hard to put like a hood over your batteries and collect that and have it vent to the outside. Even if you had like an open air structure, if it had a vented roof cap, not a sealed roof cap, but a vented roof cap, that would be enough for the hydrogen to float up to the top of the room and then get out of the roof cap, as long as you had some airflow in the building. Maybe even without airflow, it would still work. But there are ventilation requirements that are intended to prevent the hydrogen gas from accumulating anywhere in the building. Now, what that means is the ventilation and air conditioning. Like if you have your batteries in an air conditioned room, that will be fire code compliant because you have an air handling system, but you have to make sure you're actually using the air conditioner. So if you're not using the air conditioner in the spring or in the fall, you still need to be blowing that fan through the room and circulating the air. So we're going to look at the fire code requirements in a minute, but sometimes you can piggyback off of your existing air handling unit to meet that ventilation requirement. It actually depends which fire code you're using on whether or not that's acceptable. So there's really two fire codes you need to look out for. One is International Fire Code, and the other is the NFPA. And so the difference is International Fire Code is a little bit more stringent than NFPA. And so there's two requirements in International Fire Code for your your off-gassing batteries. The first is that the ventilation system shall be designed to limit the maximum concentration of hydrogen to 1% of the total volume in the room. Hydrogen becomes explosive around 3%. And so, this is what your just normal air handling unit, if it's clicking on every half an hour and blowing air through the room, and the hydrogen gas has a path to leave the room, like a hood that goes upwards or upwards out the side of the building, that would be enough to get the hydrogen gas out. But the other part of code is a little bit harder to meet for IFC. And they say, well, it's not just that you have a ventilation system that clicks on every 30 minutes and blows the air out of the room and prevents that hydrogen gas from accumulating in amounts greater than 1%. What we also need is a minimum amount of continuous ventilation. And that is what an air conditioning unit is not going to do, is provide continuous ventilation. Well, maybe some variable speed air conditioners will provide continuous ventilation. But this is where it says, shall be provided at a rate of not less than 1 cubic meter per square foot of the floor area of the room. What you'll often get is a dedicated battery box with a fan inside the battery box to blow air through the enclosure of the batteries to make sure that the area around the batteries is continuously vented. So it's more just common to locate the batteries in a room that is adjacent to the outdoors, and then put a box, even if you're inside of a garage or inside of a room, to just enclose the area where the batteries are and vent directly to the outside, even if the room is otherwise air conditioned. Some other requirements of your battery room, you have to prevent access to unauthorized personnel. So you can't just have your batteries hanging out in your garage. They can be in a locked closet in your garage, but they can't just be in your garage. That's dangerous. Um, must provide spill control for the batteries. So generally, you're going to want to put a pan underneath the batteries. And so it might be easiest to have the batteries up off the ground by an inch or two so that you can put a drain pan underneath. Ventilation, signage, and then your sealed batteries don't have the ventilation requirement. So if you're in an apartment building or a very deep basement, or if you want to put your batteries in an attic, it would be pretty easy to vent to the outside. But some siting reasons may force you into a more expensive sealed battery. Not usually an issue with off-grid. Usually with off-grid you have space. Now the NFPA is a little bit more lenient than International Fire Code. NFPA lets you do either or. You can either have continuous ventilation or non-continuous ventilation that is still designed to limit the hydrogen in your room. So putting your batteries in an air-conditioned room can meet NFPA without continuous ventilation. Still probably a good idea to have that continuous ventilation in there. There are additional battery requirements in code for more critical buildings, where there's small children. There's a requirement that the batteries be controlled to maintain temperature. Flooded lead acid has a better temperature tolerance than lithium ion. You pretty much have to air condition a lithium ion battery. You don't have to air condition a lead acid battery, but it's still a good idea to have your whole battery inverter, battery system to be air conditioned. Here's why. Your battery inverter efficiencies drop the hotter it gets. And the inside of that inverter cabinet gets hotter than ambient. So if you have an ambient of 70 degrees, you still could have 77 degrees is about 25 degrees Celsius. Even if you have an ambient temperature of 25 degrees Celsius, the inside of that inverter is going to be hotter. And so, as ambient temperature rises, that inverter can't radiate its heat away as fast, and the efficiency begins to drop. So it's a good idea to have the battery inverter in an air-conditioned room. As far as the batteries themselves go, batteries, if they get hot, it's not good for the battery. They degrade faster at hotter operating temperatures versus room temperature. So this is for a lithium ion battery, but it's true for lead acid as well. They'll actually gain a little bit of capacity at hot temperatures, but that still doesn't mean it's good for the battery. On the other hand, with batteries, you don't want them to freeze. Now, the battery can take below freezing temperatures, but only when it's charged. If it's completely discharged, the electrolyte can freeze. If it's charged up, the electrolyte won't freeze even below freezing point. And so what that means is in the wintertime, you can't have your batteries, if they're outside in a box, get below freezing and be discharged to more than 50%. At that point, the electrolyte begins to freeze. Well, we've seen there's some winter conditions where we might be going all the way. That's when you would be going all the way down to the bottom range of your batteries. So that's not, if we want our batteries to be in a cold environment, we have to prevent them from freezing. We'll get longer life out of our system. We'll get more efficiency out of our system if they're in air conditioning. And so what that does is it kind of begs for the whole system, the batteries and the inverters, to be in a temperature controlled environment. In fact, I've even heard installers say that if you have your batteries in a hot box, but there's a concrete slab that's on the ground that might be cooler than the temperature of the rest of the box, just that temperature differential alone can degrade the batteries faster than otherwise, because the bottom of the batteries would be cooler than the top of the batteries, and that temperature differential causes different degradation rates within the battery itself. And because usually a 12-volt flooded lead acid battery is comprised of multiple 2-volt cells. And so the cells at the top of the battery stack being hotter than the batteries at the bottom of the battery stack being cooler have different electrical characteristics. And that means they're going to age differently. And that means, the cells are going to go bad a little bit faster than otherwise. So, on the one hand, your lead acid batteries are easier to locate outside of the house, whereas lithium ion needs that temperature control. It's less temperature tolerant. On the other hand, even though the flooded lead acid batteries can take the heat and cold a little bit better than lithium ion, you still want to temperature regulate them. And then I take that a step forward to say, well, you also need a lot of water for filling up your flooded lead acid batteries. And one thing that air conditioners create is distilled water. So I don't, on my $50,000 off-grid systems, we're now building sit board boxes around our batteries and putting everything outside in the box, and then putting in a dedicated air conditioner unit inside that box to meet the NFPA requirement, and also generate water and also temperature regulate the inside of the box, even though we don't absolutely have to. The electric vehicle industry has shown that even if you don't have to temperature regulate your batteries, it's still a good idea to. All right, so perhaps the most complicated part of an off-grid system is allowing enough space for the batteries to go. In fact, both of these pictures that I'm showing you have electric code violations in them. And there's a few. So for one, you need working space along the batteries. And it depends on whether or not you're up against a wall or up against other electrical devices on what that working space is. But it's generally speaking is about 3.5 feet. The width of the working space, this is actually the easiest one. It's a minimum of 30 inches or the width of the equipment. So normally you don't have to worry about the width of the space, so of your electrical devices. The height of the space, 6.5 feet, or the height of the equipment, whichever is greater. One that I see, it's very easy to think, okay, well, here's where my batteries are going to go. And then I have to land all my inverter equipment. And why don't I just put this this is all electrical space here. It's dedicated electrical space. So let me just put my service panel right there. Well, there's another dimension, which is depth. You know, how far out this is, because, you know, if you needed to get to these breakers in here, you need to open up that cabinet, and then you're leaning over the battery cabinet. National Electric Code actually says, no, you only have 6 inches of differential between one electrical box that's above another. So this is actually a code violation because we don't have that. It violates the 6 inches of depth. Well, then it comes back to battery maintenance. I mean, this is the #1 error. Yeah, I've made this before. You know, you have the room that the stuff's going to go in. It's very tempting to just shove these batteries up against the corner of the room. But we have to remember, we have to take our hydrometer and stick it into these batteries as part of our maintenance cycle. Now, you don't have to test every single battery. So for mine, I have, on one of mine, I had 8 batteries, and they were comprised of 6 cells each. And so it's fundamentally there's 48 spots that I'd have to stick my hydrometer into. You know, the battery manufacturer says, no, what you do is you just test 1 cell per battery, and then the next year you test the next cell. The next year you test the next cell. And so you know, you're not sticking the hydrometer into every single hole inside the top of the battery, but at some point in this battery life, you're going to have to get right here and stick your hydrometer into there and measure the specific gravity of that battery for warranty compliance. And that is not an accessible location. You know, you don't have your 3.5 feet of working space because you're up against the wall. So that's a code violation. You know, just taking your batteries and taking the long end of them and putting them up against the wall. You know, I'm not sure an inspector would know enough to fail you on that, but in your most kind of aggressive jurisdictions, you could fail inspection for that reason. So what does a flooded lead acid battery bank look like? Well, when we did our layout, we said, okay, well, we want everything along the same wall. Well, then we violated that 6-inch depth of working space location. So then we say, okay, well, let's take our inverter wall and have it catty-cornered, because you don't want your battery inverters too far away from your battery, because then, you know, what you want is the shortest distance possible between your battery bank and your inverter to reduce the resistance of that home run. And so then we said, okay, well, now that we're catty-cornered, the problem is we still have to access these little dots on the back of the battery at some point with our hydrometer, and that is just not accessible for this room. This is just a reminder of the different cells you would stick your hydrometer into. So you can see these different holes for each cell. That's what your watering system is plugged into. So we're going to come back to the array layout in this slide, but another thing to keep in mind is that your charge controllers and your battery inverters tend to be larger than the solar batteryless inverters today. So you have to remember, the solar batteryless inverter market is the solar market for the last 10 years. And so they've what used to be a large clunky inverter that weighed 50 pounds is now a small little lightweight inverter that weighs 30 pounds. Well, your battery inverters have more stuff in them, and they're back in that larger, clunky, heavy form factor. And if you're double stacking them with a dedicated service panel, so this is a Schneider service panel, and it actually has a AC side and a DC side, and the charge controllers come and land on the DC side, and the battery bank comes in and lands on the DC side, and the inverters come and land on the AC side, and the generator and the grid come and land on the AC side. Well, so now you have a service panel, a couple of charge controllers, and maybe 2 battery inverters for double redundancy. All of a sudden, you get into that's for the Schneider system, which is one of the larger systems. That's a 8-foot wide stack right there. And I'm a big fan of this stack for a luxury, larger home. And the batteries themselves are large. These industrial flooded lead acid batteries, let's see, we used this one right here. 1,000 amp hours, 12 volts, about 12 kilowatt hours each. Goes up more than that. But you can see it's 38 inches. That's 38 inches tall by 10 inches wide by 25 inches deep. And we had 8 of these things. And so our battery floor space, the width of the battery, 8 inches times 8, 64 inches, that's going to be over 5 feet for the battery bank. And they're going to stick out 25 feet from the wall, or 2 feet from the wall. And then this is 8 feet, and it's only going to stick out 9 inches from the wall. And so, we can't really just have them up on the same wall either. So we're going to come back to our final array layout, but a couple of other considerations to keep in mind. Well, one is the batteries your lithium ion batteries have to be listed for purpose. And so if you want to buy a used electric vehicle battery and go off grid with that, just keep in mind that's going to be a code violation. Somewhat interestingly, the listing requirement does not apply to lead acid batteries because they're lower voltage, I guess. In fact, there's fewer requirements for these lead acid batteries that are rated for 48 volts up to 60 volts within National Electric Code. Your lithium-ion battery circuits, they all need disconnect switches on them. You don't necessarily need a disconnect switch on both ends of your battery terminal. When do you need a disconnect switch on a battery terminal? So basically the disconnect switches need to be there if the battery bank and the inverter are not right next to each other. Let's say you had them in different rooms. Let's say you had an outdoor battery cabinet, but you put your inverter indoors right on the other side of the wall. So you go through a wall with your battery conductors. You'll need a disconnect switch at that point. And so if you have if the batteries go through a wall, if the batteries are more than 20 feet away from the inverters, that's when you start needing to have serviceable disconnect switches for your flooded lead acid battery banks. Some other requirements, deterioration. Supposedly this hydrogen gas that the batteries emit has a deteriorating effect on metal. Now, I've asked a few installers who have more experience than me on this stuff, and they've never seen metal deteriorating because of their off-grid flooded lead acid battery banks. They say, well, there is some corrosion, but if there is, it's usually around the battery terminals and not, surrounding metal because of gas. But that means your metal needs to be, have some kind of deterioration resistance, whether it be an anodized metal or a painted metal or a plastic coated metal to be compliant with code. But paint alone should not be considered an insulating material. And if you build your battery rack out of metal, which is common, you need to put a non-conductive support between that metal rack and the batteries. And that is a danger that I have heard reported, where the voltage from your batteries, if you just go and put them onto a metal rack without any insulation, you gotta, like on an industrial flooded lead acid battery, you have a metal cabinet, and that voltage can leach out of the batteries into the metal racking. So you have to ground your metal racking, you have to insulate between the batteries and your metal racking, and you also have to paint the metal racking if it's unpainted with no anti-corrosion treatment applied to it. Then there's another section for not just batteries, but true energy storage systems in National Electric Code, applied to batteries that are over 60 volts. So this is more written for lithium ion battery requirements. And like we talk about in our National Electric Code, a lot of the requirements that are in the specialty sections of code near the back are simply reiterations of requirements that appear in the more general sections towards the front. And so it says, hey, here we reiterate the ventilation requirements. One thing that jumped out at me is, even if you don't have to access the batteries for maintenance purposes, you should put a 1-inch clearance between any wall and your battery bank. So a little bit more requirements for higher voltage batteries than there are for low voltage batteries. Here is a plastic wrapped metal conduit. We have to remember that code requires DC circuits inside of buildings to be contained in a metal raceway. And then that metal raceway can't be exposed to the corrosive gas of the batteries. And so this is called a liquid tight flexible metal conduit. It's the most expensive kind of flex conduit. So you can buy metal flex that doesn't have this plastic wrapping. You can buy non-metallic flex, which is really just this wrapping. You combine the two together, that's where it starts to get expensive, but that's kind of the nicer product for running your battery cables through back to the inverter from your battery enclosure. Where DC circuits run into a building, they shall be contained in metal raceways and have a disconnect at the first readily accessible means. Well, how this applies, this is a solar requirement, but how it applies to batteries is, if you go through a wall with your battery bank, you need a disconnect switch on both sides of the wall. Even on our 48 volt battery banks, they go all the way up to 57 volts at full charge. So, they're rated for 60 volts. You charge them up to 57 volts during the maintenance process. It kind of busts any plaque that's accumulated on the anodes of the batteries. Overcharging the batteries can be helpful as long as you don't overcharge them to excess. So periodically, every 2 weeks during heavy usage seasons, maybe once a month, off season, you overcharge them for conditioning. And so your batteries have to be protected. A very easy way to do that is keep them in a locked room. You could elevate them above the floor, put them on an elevated platform. So again, this really only applies to the higher voltage batteries. But it says where the energy storage system outputs are more than 5 feet from connected equipment, or where they pass through a wall or partition, you need to have a disconnecting means at the end of the circuit, or you have to have a second disconnecting means where the disconnecting means is not within sight. So now we finally get into having a disconnect switch on each side of the wall. I suppose technically you could get away with this being a lead acid battery instead of a lithium ion battery, but these safety reasons are there for a reason, regardless of if it's high voltage or regular voltage. And what it really is kind of implying is that you want to try and design your battery bank to be within 5 feet of your battery inverter. And so coming back to our array layout, kind of the most space compact layout you can get is having the short end of the battery up against the wall so that you have enough clearance space to work on the front end and then walk around on the back end so that you can actually stick your hydrometer into any point of the battery. And so whereas if you did this long ways or against the wall, you wouldn't be able to access the back of the battery. And so what this really means is you take the length of the battery and then you add about 3.5 feet on each side, and then you can hang your 8 feet of inverter equipment on this side. And so what that really means is if your big giant industrial flooded lead acid battery bank is 10 inches wide and you have 8 of them, that's 80 inches. That's going to be 7 feet. And then you need to be able to walk around it. And then your inverter equipment for this particular Schneider layout was 8 feet. And then we need, because it's electrical equipment on both sides, we need 4 feet of space here. Because you're not up against a wall and there's no electrical equipment on this side, you only need 3 feet of space here, but these batteries are 2 feet. And so we got a 2-foot battery. We got 4 feet of space here. If we were up against the wall, we would have 3.5 feet of space here, and then about 6 inches for the rest of our equipment. And so what we're looking at is 4, 8, 9, 10. This really says that our battery room dedicated space is really about 10 feet by 10 feet for a room with all of our battery equipment in it. Or if you were building a battery box for this type of system and you had it outdoors, you might want to keep it 3.5 feet away from the side of the house just so that you could open up the box and maintain it on all sides. Don't err by putting it right against the wall of the house and having to, because you can't reach over the 2 feet of space and access those cells for testing the hydrometer. What easily happens when you're leaning over a battery bank is you can drop things into the battery bank. And that's how accidents happen. A necklace, a wrench, that all could fall into the battery and touch terminals together and cause a disaster. You could, if you weren't doing 2 inverters, if you're only doing 2 charge controllers. If you didn't use the service panel, but were just using the landing terminals on the inverter itself, you could have a battery box and then, use one side of the short end for your inverter equipment and then fully enclose it. What we're looking at for our next iteration of our battery box design is putting in a water tank here as well and making it something that is quite large and multifunctional. So a good rule of thumb, 10 feet by 10 feet for your batteries and inverters for an off-grid home using flooded lead acid. And then 20 years from now or longer, whenever it's time to replace the batteries, then you'll use lithium ion, which is much more space efficient, and then get all that working space back. Another thing to keep in mind, grounding for off-grid. Generally, you have a ground rod at the side of your house. So here's your house, you go outside where your electric service is, and you'll probably see a little copper wire going into ground. Well, there's also a secondary ground at the utility pole. So next time you're on a walk, take a walk, and wherever you see a utility transformer, you'll probably see a copper wire going down the pole onto a secondary ground. Well, that's interesting. And National Electric Code requires a supplemental grounding electrode. So it says whatever your grounding system is, you need an additional grounding electrode there. Well, this is not normally something you ever have to get into with a grid-tied system because you have the ground electrode for your house, and then you have that secondary grounding electrode out at the utility transformer. When you're designing an off-grid home, just put in 2 grounding rods instead of 1, and you'll have that nice double redundant connection to ground. You can't just put that connection to ground anywhere in the system. It has to be on there's at one point where the neutral of your electric service is connected to ground. And usually that neutral to ground connection is done inside your utility meter. So it's not apparent to anyone who's not into the electrical industry. But that little neutral is a drain for your electricity. And so your electric usage is ultimately, it needs that neutral to ground connection. And so they say, well, on that other side of that main bonding jumper, you need your grounding electrode. Well, there's also a call out for a secondary grounding electrode. So 2 grounding electrodes. They can be right next to each other. Another nuance that you want to be careful when you're presenting your terminology to your clients for these off-grid systems is there is a difference between emergency power and standby power. So I have a lot of customers in Mississippi who want to do solar because they have on-site medical equipment. And they want to make sure when the power goes out that their medical equipment remains online. Well, depending on how critical that equipment is, it may be, life-supporting emergency equipment that can't lose power. And that would be an emergency system. Whereas standby is like, well, the power's out and I want to run my air conditioner. That's a standby system. That's not life-critical. Well, emergency power systems have harsher design requirements. One common one would be using rigid conduit rather than flexible conduit. so that if a car hits the conduit or you're drilling willy-nilly through your wall, you can drill through EMT conduit quite easily. Rigid conduit provides more protection. So I'm very careful to say, where this could trip you up is you might tell your client, oh, you'll lose power during an emergency. The solar wordsmith would say, oh, you lose power during a disaster. Try and avoid the use of the word emergency unless you're truly providing a system that is compliant to the emergency conditions of an EC, which are typically more robust protection for your cabling. This is another thing that starts to explain why these grid-tied battery inverters are so weak, for lack of a better word, is there's a requirement that says if you're going to have an automatic transfer equipment, whatever your standby source is, it needs to be capable of supplying the full connected load. And so if my battery inverter is like the SolarEdge storage inverter, it's not capable of supplying a 200 amp residential home. It's only capable of supplying 25 amps at 240 volts. And so that's why with your StoraEdge, with your grid-tied battery systems, they say, oh, we're going to have an automatic transfer switch built into our inverter, and you're going to install a dedicated load panel with just a few loads that you're trying to power, and that's going to be our standby power source. And because it says you can't just put a 40 amp standby power generator on a 200 amp electric service, because you're not going to be able to supply the load. The AC turns on, it sucks all the electricity out of the wires for the rest of your circuits, and your whole power system goes out. It's undersized for the standby system you're trying to power. And while we have manual transfer switches to say, okay, well, during Hurricane Sandy, I'm going to go buy a generator and wire it up to my service panel, and I'm going to go manually flick the interlock switch and turn my generator on and supply my whole house. And I'm just going to make sure if I have a 10 kilowatt generator and I have 40 kilowatts of breakers, I'm just going to manage my electricity to make sure I can supply the power to it. This is an automatic transfer switch requirement. And so we see a lot of automatic transfer switches in these grid-tied battery inverters, and they're not supplying the whole house because they're not rated to. All right, we're going to take a break in just a minute or so. Let's keep moving on because it's a full day of class. This racking part really doesn't have as much to do with off-grid as the rest of the sections. So, I really just included it to provide a little bit of advanced racking knowledge that you don't get in some of the intro to solar classes I teach. So basically, when I'm doing my designs for racking, even if I'm designing with, say, a 4 foot on center, or even my spans and sometimes go for 6 feet, sometimes 6.5 feet. When I do my designs, I recognize that the top and the corners of the array are experiencing higher wind load than the interior of the array. And so when it depends on the roof surface, but shingle rooftops are actually a pain in the butt because you have these shingles, and then you have to slide a metal plate with a screw for the lag screw underneath these shingles, and then the shingles are nailed into the rooftop. And so you have to take a crowbar and being careful enough not to rip the shingles, you have to pry up the roofing nails, not adjacent to the flashing, but just where they're going to conflict with the flashing, and then slide them up into there. And so a shingle rooftop actually takes longer to install the racking on than a metal rooftop where it's a little more, you're not flashing it. You're just doing I actually think that the metal rooftops are more waterproof than this retrofit shingle process, but that's really a topic for another time. The reason why this is all important is because the standard layout for your attachment points is just to go 4 feet on center. And then for style and for better distribution across your truss, you will stagger them. So here we have a 4 foot on centered layout where from one row to the next, the attachment points are staggered every 2 feet on center. Well, okay, but the rail itself is rated commonly for a 6 foot or maybe even a 7 foot span. And so what I'll do on my shingle roof designs is in the interior of the array, I still stagger my L feet, but I only go to that longest span in the interior of the array, whereas on the exterior of the array, I put additional attachment points at the corners to give it a little bit more strength. And then if you are in an area where there's heavy snow, the other thing to watch out for is snow will mound at the bottom of your array, and it'll transfer more weight to the bottom of the rail of the array than the top. And so what you get is more load on these bottom attachment points than you do on the rest of the array. So if you're in an area where you get heavy snow, that's where I would do 2 foot on center all the way across the bottom rail. Like if I'm in Buffalo, New York, because the weight of the snow can crush the bottom rail through your rooftop, even if you're within spec. There's no failure in the racking. The whole solar array stays in one piece. The failure is in your roof decking. And so you want to go beyond the racking spec to make sure you're distributing that weight as evenly as possible across the bottom rail. All right. Welcome back. Again, we're kind of covering some advanced racking issues. This was the design that came to me from a developer. And they were doing a few things that I had not seen before or really considered in my game, which was providing a maximum tributary area for rainwater runoff. And that started to get me thinking, well, this is on a metal rooftop, so it's not as big of a deal. But what if this were a shingle roof? Shingles, they get a even amount of rainfall, but now we have a big shield on top, and that water is going to slide down that shield and then all come in at the bottom. So all of a sudden, this row of shingles that's right underneath the solar array is going to get substantially more rainwater runoff than what that shingle was used to. And so I like taking my array and where shading allows, making sure that it runs kind of from the top of the roof all the way down to the bottom, or starting my array row right along the bottom of this roof line area to make sure that the rain or snow on top of a solar array doesn't land and degrade the shingle right along the bottom, but to actually go into the gutter or over the side of the roof, and not, because that would stink if you had this whole roof and the solar array protects the shingles from sunlight, but now you've inserted another reason why they would degrade, which is rainwater runoff. And all of a sudden, this row of modules becomes kind of a torrential rain zone, and that little edge of the shingles might degrade. So I haven't seen this pop up in the solar industry as an issue of concern, but I think that might have to do with the youthfulness of the solar industry. Maybe in 20 or 30 years, we start to see some complaints about how, they have to replace the roof because the rainwater from the shingles is degrading that bottom shingle layer. So consider how rainwater runoff is going to be impacted on your design. I also didn't like this design because it would get shading from these dormers. So we went with something that it was further away from the dormers, less exposed to shade, and on a metal roof, it's not as big of a deal. This is a wiring technique that I came up with for the Solar Edge system. When I'm picking out my solar racking, what I really like to find is a solar rack that has a U channel in the rail. Sometimes this rail is instead like a more solid bar, and you have to get little clips that hang off the side of the rail for your home run cables. I don't like that. I like the U channel because what this U channel becomes is kind of a raceway or cableway for your wires up on the rooftop. And for that matter, it also, if you have this U channel that you can slide your solar cables into, it acts as kind of a guard against squirrels and critters and stuff like that, for kind of maximum protection. And so what I do with my Solar Edge DC optimizers that are mounted behind each module is I'll get that U-channel rail, and then on the ground, I'll pre-assemble the entire rail, and then I'll go ahead and mount the optimizers to the rail, and then tie wrap that cable into the channel. And then the problem always becomes, well, what happens when you mount the module on top of it? So the module is going to cover that, and the module has a junction box, and the junction box has two whips of cable that then get plugged into the optimizer, or if you're not using the optimizers, they get plugged into their next door neighbor. But the Solar Edge optimizer system is a very popular one. Like, it's probably the most popular system in the United States. And it is always a challenge when you're mounting the module, because it's like, even if you do the best tie wrap cable management in the world here, you still have all this loose cable that gets plugged in to these whips. So how do you manage that cable? Any kind of loose cable on the rooftop, not only is it a sign of a bad install, it's not done workmanlike, but any exposed cable becomes a target for squirrels to chew up. The solar industry has cable management clips available. This kind of metal clip will clip onto the side of your module frame or the side of your rail, and you kind of press your solar cable into this cavity to do some nice tight cleanup. The problem is, when you go to mount your module, you might need to tug on the cable that you've already clipped to the module frame, and it might pull out of the clip. And so the clips are not a perfect system. But zip ties are not perfect either, because they can degrade and become brittle and snap. And then if that snaps, then you have loose cable spilling down onto your rooftop as well. And so I've developed a system where normally the optimizer is right underneath the module, and then you just kind of bundle the cable up underneath the module as you're laying it down, and just kind of positioning it so that it's all between the optimizer and the rail and the module frame and not completely underneath it, spilling down onto the rooftop. Lately, what I've been doing is instead of locating the optimizer behind the module, I put the optimizer behind the next module over. I call it hopscotching it, as it's like a half step over. And the reason being is because in this what I call a hopscotch configuration, you mount the module and then there's little clips that clamp the module down to the rail. And so what this lets me do is before plugging in to the optimizer and module, it lets me completely mount the module, and then I can reach underneath and pull these whips out and plug them into the optimizer. And by simply kind of wrapping the two module whips around each other, that gets rid of all of the slack in the cable. So you no longer have these droopy loops of cable that can kind of sag down and become exposed underneath. And so I put the optimizer underneath the next module over and then twist the cables around and snap them in. And that cable management gets rid of any slack in the cable without using cable clips or tie wraps. You know, I've already put a little bit of tie wrapping in to get this cable into the channel, but once the modules are bolted down onto the rail, the module frame itself secures any cables that are in this channel to be there for the long haul, because the module frame itself now prevents the cable from popping out of the channel. And so, you know, with this technique, by locating the optimizer, the next module over, by pre-assembling the rail and the optimizers before lifting it up onto the rooftop, it creates this kind of perfect cable management opportunity. And then on the very last module on the row, you just have two optimizers underneath it. The last optimizer gets plugged in as normal. And then I'll also locate the transition box underneath that array so that this gets plugged into the transition box for your home run. So the home run cable kind of looks like that. It stays in the channel of the rail, except for that very last run where we're transitioning into the roof for our home run circuit. And so this is the net effect of my hopscotch cable management technique. And I think this is kind of the litmus test of a good solar installer is being able to look underneath the solar array and to be able to see all the way across to the other side without any cables dropping down. And so there's actually quite a bit of cabling underneath this solar array, but because we selected a rail with a U channel, we've been able to tuck all of the cable into that U channel, and then you know, kind of before we even bring the stuff up onto the roof, and then we have this twisting technique to take out any slack of any other loose cables, and that keeps the optimizers are right here, and that keeps all the cable whips right tucked up next to the optimizers before they transition into this rail, kind of nice and neat. There are some racking systems that are called shared rail racking systems. So normally you have like 2 rails per row of modules. So it says, well, why can't we just move this rail up a bit and share it with the next row of modules? And that's called a shared rail system. And so, you know, most solar installers don't use shared rail systems, but shared rail systems would have 1 less rail per 2 rows of modules, a little bit of labor savings. You know, where I have found shared rail systems to be useful is on metal roofs with purlins. So the purlin, usually you have rafters that run kind of north-south that you're lag screwing into, but on a metal rooftop, You might have some, let me see if I can't draw it. You might have some rafters running north-south, but then on top of that, on top of the rafters, you have these purlins that run east-west. So there's actually a gap between the rafter and the roof surface, and your lag screws have to go into the purlins rather than into the rafters. Well, that gets a little bit complicated because these purlins have a defined spacing in them, and there's certain clamping zones in your module spec that you have to keep your clips within those zones, otherwise it is out of spec. And so just know that on a purlin rooftop, if you're having trouble maintaining the clamping zones of your array, to consider a shared rail system. And so what I'm thinking about, and what I really need to have is probably a blank slide to draw this on. But what I'm thinking about is I had a system where I really only had in my rooftop, I only had 3 interior purlins running across the rooftop that I could mount to. And so a shared rail system was perfect because I had 2 rows of modules and only 3 purlins that I could mount to. And so I couldn't have 4 rows of racking running across the roof. I could only have 3 rows of racking of rail running across the roof. So, shared rail systems are kind of specialty, but they are available. They're kind of the same price as if not a little bit cheaper. And one advantage of that is if you usually on a shared rail system or on a metal roof with purlins, you need to go in and reinforce where the purlins are attached to the rafters, because the purlins are just nailed into the rafter, and now you have a lot more force on that purlin, and the nail on the purlin may not have sufficient pull strength for it. And that's no problem. You just need to go put little L brackets between the purlin and the rafter, and just screw the purlin into the rafter to make sure it's a solid connection. Well, that's annoying to do on every single purlin or every single rafter. Attics are not comfortable spaces to be in. And so like on this type of system, what we would do is share the middle purlin going across, and then only go and reinforce the middle purlin to the rafter underneath it. And so we're not adding additional attachments between the purlin and the rafter for every single purlin and every single rafter across the roof, but through creative use of a shared rail system, we get some structural advantage. When you are putting in these flashings, the general rule of thumb is to go and identify where the rafters are, and then snap a chalk line up and down the rooftop to identify where the rafters are, and also an east-west chalk line to make sure your lag screws are exactly where they need to be. It can be kind of tough to identify a rafter, particularly on a shingle roof. On a metal roof, it's a little bit more straightforward because you can see where the metal roofing screws are holding on the metal roof into the truss underneath it. On a shingle roof, it's a little more hard, and there's really no perfect way. You could use a stud finder, but a $50 stud finder won't cut it. There's a $1,000 stud finder you can use, but it's still not a perfect process. Stud finders don't like these uneven surfaces. And so it's, even if you went and bought the highest end stud finder on the market, it's only going to get the rafters identified through a comp shingle roof. It's only going to be an assist. You're not going to be able to pick out every single rafter going across the roof line. So what most installers that don't have this $1,000 stud finder will end up doing is taking the back of a hammer and tapping across the roof and kind of hearing where the rafter is by rapping the roof with the hammer, which again is not a great process for the rooftop, and it will lead some false positives as well. But generally, by tapping through the top of the roof, I take a little whiteout pen and mark where I think the rafters are going to go. And then I go down the roof and I do it again in about 3 places and then see where and eventually you can get into that attic and understand that the rafters are either 16-inch or 24 inches on center. And based on where you've kind of guessed where the rafters are going to be, you take out your ruler and start measuring, and they start to correlate with whatever kind of rafter system you have underneath. The other recommended method is to go into the attic and actually measure the spacing for the rafters, but you really can't do that unless the attic is incredibly accessible. So most installers will use the hammer method. Then you drill a pilot hole. So the lag screws are pretty thick. So you take a thinner drill bit and drill through the roof, and you'll be able to see at that point if you hit the rafter or not. If you didn't hit the rafter, that's a good time to get back into the attic. If you got to the side of it, get into the attic, find where that hole is, and then measure how far you need to go to actually get to where you need to be. But obviously the point is not to guess too many times going across the roof. Now the flashing does kind of cover a lot of sins. But the point is there's no truly perfect process for identifying where the rafters are. A little bit of field experience does help with that. You can see on this past picture, we didn't really have a good strategy for managing this conduit across the rooftop, and we kind of strapped it to the roof. There is, I learned later, a product that S5 makes for elevating conduit up off of a metal rooftop. So I think that's pretty cool and worth looking into. Another common mistake that I see on metal rooftops is with standing seam. I don't really understand standing seam and solar, because you put an expensive roofing system on and then you cover it up with an even more expensive solar facade. A cheaper corrugated roof is just as good. You don't need the expense to get that standing seam. Well, okay, but standing seams are popular. And so there's a company called S5. They make a little clamp that goes over every seam and forms the attachment for your solar array. The problem is most solar installers, they're not going to want to put a clamp on every single seam. And so they skip them. And then the problem with skipping it is your standing seam metal rooftop, the clip that attaches the roofing panel to the wood underneath it is not rated for putting that much concentrated force on any one given panel. So you go and you read the S5 racking documentation, it says to put a clip on every single seam as you're going across the rooftop. A lot of installers skip that. I just, watch out for that. The reason why an installer might skip it is because it takes time to put that extra clip there, but it's also costly to put that extra clip there. And so they think, oh, I'm going to save money by, standing seam by just having a handful of clips to clip the modules on. By the time they run the cost for clipping to every single seam, there's really no cost advantage of going with a railless racking system on a standing seam metal roof. But that's what the manufacturer spec says. Here's where we're transitioning into the rooftop. And there's a couple of different ways you can do this. The common way is to get a specialty box that's a flashed transition box. So you drill a hole through the rooftop and you knock out the hole in your box and you line it up just so. And so what I'll do with my home run cables coming through the attic is shove them up through that hole and land them on a terminal block, and then take the cables from the array and land them on the other side of the terminal block. And that's I'd say the most common quality way to do the transition. But we have to remember solar is not the only thing that pokes a hole in the rooftop. And so you could just as easily get a flashed roof jack and put that on the roof instead and just dispense with the box. Now, the problem with most plumbing roof jacks, and I'll often get my roof jacks at plumbing supply stores because I find them to be a little bit better quality than what you can get at a box store. Most plumbing stores will allow just walk-in counter purchases. You don't have to be a contractor to buy the products there. Electrical contractors sometimes are a little more iffy. But here we have a flashed roof jack. The only problem is plumbing roof jacks tend to be a wider diameter, like for a 2-inch or a 3-inch pipe, whereas most solar conduit coming up to the rooftop is going to be 3/4 inch, maybe 1 inch. And so there are kind of specialty roof jacks that you can buy in the solar industry if you don't want to have the box, if you just want to shove the conduit up through the roof jack and then keep going out to the array. I'm a big fan of MC cable for solar. The DC has to be in metal. Well, MC cable is a metal clad cable. So that takes care of the metal requirement. The main problem with metal clad cable is it's only rated for damp conditions. It's not rated for wet conditions. And the rooftop is a wet condition. The side of your house might be wet, might be damp. Generally speaking, here's your roof, and we're putting, if we're putting the inverter outside, we hang the inverter on the wall, and then we run up into the attic. And then with this MC cable, you can just kind of string it along the attic and then go up into your box. And even though technically speaking, this little whip of MC cable is up on the rooftop, it's enclosed in a box. So I haven't had any problem with inspectors, saying, oh, well, that's a wet condition environment. It's fully enclosed in the box where the solar array is, and I kind of hide it underneath the module for aesthetic reasons. Well, this whip of the MC cable is protected by this awning, so it's not going to get any direct water spray. But you have to be careful with that because the further down you go with your MC cable, the more likely it's going to be exposed to sprinklers and water spray and stuff like that. But MC cable is certainly an easy way to run internal conduit through an attic. In fact, what I'll do is I'll go and upsize my MC cable to number 6. And the reason why I upsize it to number 6 is that way it comes with a number 8 ground. And the number 8 ground is the minimum size for the ground conductor that runs up to the solar array. And so I'll get a number 6 MC cable. Either I'll get 6/4, which would give me a positive and negative, another positive and negative for another circuit, plus my ground, or I'll do a 6/2 for just one circuit and run that between the inverter on the side of the wall and my transition box up on the rooftop. That's another sign of a quality install, in my opinion, is if you have an internal conduit run rather than an external conduit run. So far, I've only landed on transition boxes into the rooftop, but one kind of advanced technique that I'm looking at is ending my MC transition in the attic and then transitioning to a short stub of EMT with a threaded 5-hole connector on top, where I could dispense with everything at that point and then just have at this point my cables come out with my MC connector and just kind of shove the last whip of EMT through a roof jack and then plug in to my solar circuit. I'd love to go into more detail on this stuff, but these are the custom connectors for solar called MC4 connectors. And so generally speaking, I'll take on my transition box, I'll make MC4 whips and land them on the terminal block and already kind of just pre-make this box as much as I can so that the install crew, once we know where this transition is going to be, we drill the hole, mount the box, and as the install crew is mounting the array, they can just plug in to the MC4 connectors just like they would do on a normal install. Ground mounting is changing too. What is most common with ground mounting is to get a bobcat with a big giant auger and then auger out some holes into the ground and then fill those holes in with concrete. So you get a pile that goes down into the hole and gets concreted into the ground. And so you're renting the bobcat, you're renting the auger attachment, and then you got to get the concrete to the site too, which sometimes can have its own logistical issues. It's not so much the cost of the concrete that's the issue as just one more thing to coordinate. But ground screws continue to make ground. And what I learned recently was that ground screws, so what these do, they're depending on the soil type. So this is a ground screw where you have a little bit of rock in the soil, whereas this is more for like a sandy clay type soil. And that ground screw will give you enough pull strength to hold your solar array into the ground. It's not enough strength for like the foundations of a building. But if you're doing a ground mount solar array, I would look at ground screw systems mainly because now you can attach the ground screws to the auger of a bobcat and then just screw them directly into the ground. So how this would work is you could have some uneven ground, and then you take your ground screw and screw it into the ground and then just kind of lop off the top to make an even platform to mount the ground mount solar array to. And so like at the utility scale, they take piles and a pile driver and just hammer the piles into the ground and dispense with the concrete that way. Still possible at the residential level with a bobcat with an auger attachment and ground screws to dispense with the grading and the concrete for your site. Another problem with the concrete forms is often they're going to require a depth of about 6.5 feet for standard soil types. And the problem with a bobcat and an auger attachment where you're drilling out the foundation to pour your concrete into is with the bobcat and the extension bit and then the little auger to drill that hole, it can only go down just short of 6 feet. And so if you're planning on doing concrete foundations for your ground mount and you're not going above ground with either like a sonotube form or building your own concrete form, you can't quite get to spec with a bobcat and an extension bit and an auger attachment for most ground mount systems. So that's kind of the problem with concrete and just putting a post in the ground and concrete it in the ground is you're almost asking to be out of the manufacturer spec just so. And so bringing the conversation back into off-grid, the real question is, do you want to have a tracking ground mount if you're going to do a ground mount? The way I look at it is every utility scale project nowadays does single axis tracking, not north, south, east, and west, but the modules will track the array from sun up to sun down. And so the solar industry says, oh, well, tracking's not cost effective. Instead of tracking, just buy more solar panels. Okay. But is that really true? I mean, obviously there's some point where tracking does become cost effective. I'm going to digress for a moment. This is another utility scale technique where they use 72 cell modules, and that'll allow them to skip over every other module. And then they get to the end, and then they come back skipping over every other module. And that makes better use. It's not so much that you would have to build a home run cable at this point to run back. It's not so much the cost savings of this home run cable, but there's voltage drop in this unrealized cable length width that you are now putting to work with your skip stepping technique. This is a very minor point. We don't have enough time to dwell on it. One thing that I think about with ground mounting is it's almost better to do a solar edge voltage regulated high voltage return on the ground versus on the roof. The solar edge system is very popular on the roof. Now that I have this wire management technique, that was my biggest problem with solar edge on the rooftop, is the installation time and the cable management. Well, now I do as much pre-assembly on the ground and pre-cable management on the ground. And now that I have this other cable management technique for module mounting, it's not really a big deal anymore. So I like the solar edge system on the rooftop, but what about on the ground? Well, often with off-grid, you might have a house in the middle of a forest, and then the field might be 500 feet away. And once you start getting into 500-foot plus distances, well, it just gets you into the same problem that we talked about yesterday. The cost of building the grid out to that point starts to get rather costly. The cable cost alone to go 500 feet from the array, you start getting into about $3 a foot cable cost. So you can see how that can start adding up. Well, one thing that's the cable is so costly because of voltage drop. You might have a 2% voltage drop between the inverter and the array. And what that has to do is with the cross-sectional area of the copper inside that cable, the only way to overcome that voltage drop is to make it a little bit wider, give it more access with less resistance in your cable. Well, when you double the thickness of your cable, or you double the area of that conductor, you're going to double your cabling cost because there's literally twice as much copper in it. That said, all of these cable jackets and your solar cable and stuff like that, they're rated for high voltage. This is often a 600 volt return, but the jacket of the cable is rated for 2000 volts. And we know from the utility perspective, they go up to incredibly high voltage, over 30,000 volts for distribution circuits, and even more for transmission circuits, to get up into high voltage to transmit that electricity all the way back to your home before they step it down. And so why are they doing that? Why is high voltage used for transmission? Well, the thickness of your cable is the voltage drop is like the second derivative. The first derivative, the primary reason to select cable thickness is the amperage capacity of the cable. But the problem is when you're sizing your cable for a 2% voltage drop and you have to upsize your cable because of the long distance between the array and the home, you end up using, you know, a 100 amp cable for what might be an 8 amp circuit because you need to upsize it. And that's a little extreme, but it's to make a point. You end up upsizing your cable for the voltage drop, and that means you end up having a lot more ampacity capability of that cable than what you're ever using. So you're overspending on your cable budget. And the reason why utilities step up to high voltage is because, you know, power wattage is a volt times an amp. And so if you increase the voltage, you decrease the amperage. And the Solar Edge system, by putting a box behind every module, it's going to step up the voltage, and in turn, that's going to decrease the amperage. And so I like the Solar Edge platform for a ground mount solar array because it's going to increase my voltage and decrease my amperage, and that's going to decrease the cable size that I need for my home run circuit. There's more on that to come. So back to our tracking, the only reason why we don't do residential tracking is because there are almost no residential tracking manufacturers on the market. You know, there's one that does double axis tracking, and it costs about 3.5 times as much as a fixed in place system. Now, I found a single axis tracker at the residential level, and that still costs about 3 times as much as a residential fixed in place system. And those were the only 2 options I found. But when you look at the budget of a module at the residential level versus the module at the commercial level, there's barely any budget difference. You look at the inverter cost at the residential level versus the utility scale level, okay, there's about a factor of 2, not a factor of 3.5. And then furthermore, it's not expensive to do tracking. You look at utility scale tracking versus utility scale fixed, and there might be a 10% difference in project budget. Now, furthermore, I don't really like the double axis trackers because they result in giant solar arrays. And while it is kind of exciting to see a big solar array that moves in multiple directions, I question how the appearance of that giant solar array is going to age as you move into the future. Whereas one row of single axis tracking, it kind of looks more like a fence than a satellite dish. And so what I would really like to do is if I have a customer who has a tract of land and they don't have a fence along the side of their property, it's like, well, why don't we just put a single axis tracker along the side of your property, and the solar array is gonna, you know, have the same form as fencing in your property. It's not really going to take up any additional space. It's not going to be a jarring visual compared to a giant double axis tracker. Well, there's another mystery of whether or not you really even need tracking in an off-grid system. The double axis tracking company, one of their selling points is that the solar array by tracking will turn on earlier in the day, and it'll also last longer into the evening. And so they say because of that, if you're not running off your solar array, you're running off your batteries. So anything you can do to take load off your batteries is going to be cost effective. That's the sales pitch. Well, maybe so, but not if you're quadrupling your racking budget. Furthermore, does this really take load off the batteries? Because remember, this is really only an advantage on a sunny day. It's not really going to do you too much more on an overcast day, especially on those extremely overcast days that we talked about yesterday. And remember, a well-sized off-grid solar array, on sunny days, you're still going to have this stranded electricity at the top. And so, on a solar array, what's going to happen is with tracking, the battery will fill up sooner. But the battery is still going to fill up even if you weren't tracking it. So all this morning extra production just results in more stranded electricity. There is a little bit of, well, if you were on tracking, you might start using your batteries at 7 or 8 instead of 5 or 6. So there is a little bit of advantage, but it's just not a huge advantage for reducing load on your batteries. That's for east-west tracking. Some advantage, some more production, but not a huge advantage, not huge production. You can absolutely get away with not having tracking on an off-grid array. It's perfectly acceptable not to track. But that's a little bit of a different argument than saying, well, just use the budget you would spend on tracking on more solar. Utility scale tracks, you do get a morning and evening boost. What might even be more valuable is to not do morning to evening production. Remember that morning to evening production comes out of a grid-tied design philosophy where every single kilowatt hour is being sold. And off-grid, what we're more concerned about is not running out of electricity in the wintertime. So maybe east-west tracking has some advantage, but if your property line runs north-south rather than east-west, you wouldn't be crazy to think, well, should my tracking array go summer to winter rather than morning to evening? In other words, should I do north-south tracking rather than east-west tracking? Of course, there's added cost for tracking, and especially double-axis trackers cost substantially more because there's a lot more foundation work that goes into it. And kind of summarize that here. But here's the thing. When I take a step back, I say, well, is the solar industry right to discourage tracking for ground mounts at the residential level? Or how much is it that because there's not many vendors in this space and there's not much demand in this space, there's just high-priced product? Because if I'm doing a fixed array, I'm still paying for these foundational supports. And in fact, the east-west tracker kind of takes better advantage of those supports than a scaffold type build. Because let's see if I have a picture of it here. On a fixed in place ground mount array, this is a single pole where you're driving the pile, 7 feet into the ground. What's more common on a residential type array is to build kind of like a scaffold where instead of having one row, you have two rows. And I don't really like the two-row philosophy. You're kind of forced into it if you want to stay within spec. Because when you do two rows, you don't need to go 7 feet down. You can get away with going 5 feet down. And a Bobcat is capable of going 5 feet down. So you can stay within spec with two rows instead of one without using a pile driver. But it makes getting underneath the array for any ground maintenance difficult when you have this kind of scaffold underneath the array. Now, this is also for an array that is 2 modules deep. And so we take that knowledge and we apply it to utility scale single axis tracking. And what we note about utility scale single axis tracking is it's only 1 module deep, not 2. And so the utility scale foundations don't go 7 feet into the ground for a tracking array. They can go 5 feet into the ground for a tracking array. So now we don't need to go as deep, and we can do tracking, and we're not building like a bleacher system with additional rail and then the modules go on top of that. Instead, we're just putting a single pole down our row of tracking modules and then almost in a sense using the module frame as the rest of the racking. And so it's just a more cost-effective use of material to do single-axis tracking than to build a bleacher-style fixed-in-place array. And that's why they do it at the utility scale, in addition to the increased production. So the real question is, what additional stuff do you have to buy to turn a fixed-in-place array into a tracking array? And mainly, it's these hinges that provide you that axis of rotation. And then you have to buy an actuator to move it. And it's a heavy-duty actuator. And then you have to buy the control system to control the actuator. So we're looking at a control system, an actuator, and a couple of hinges compared to buying more solar modules for the same amount of production. And given that in off-grid, you really want winter production, maybe having an adjustable array that you could kick up in the wintertime for additional production, but then make more flat in the summertime for additional production in the summer too, maybe that's really the best of all worlds. And so these are called pillow blocks, and they have a little bearing inside. They cost about $20 each. Although now I've gotten pricing on industrial plastic pillow blocks, and they don't require the same amount of maintenance as a metal bearing, and they supposedly they last as long. I mean, this is not a intense application, and they get down to $10 each. Here's a heavy-duty linear actuator. I actually went to Canada to find this one. This is made by a Canadian manufacturer, and in Canada, they make very robust outdoor electronics because of how harsh their environment gets in the wintertime. A lot of electronics are rated down to -40, where Celsius and Fahrenheit intersect. Well, in Canada, it can get below -40 in the wintertime, so some of their electronics rated for -40 don't work outside. Well, this is a linear actuator that can lift 3,000 pounds. One pallet of solar is about 1,000 pounds. 2 pallets, 2,000 pounds. So this linear actuator can move the array. It's slow, but that's okay because the sun is slow. And the stroke is 40 inches. So that's long enough to get you some summer to winter or morning to evening tracking depending on how your property line lays out. And so it's really just an issue of putting a pipe cap, which you're going to have to buy anyway for your whatever kind of racking you're using, and then putting a pillow block on top of the pipe cap, and then buying an actuator. And guess what? The company that sells these actuators, they also sell the control systems for the actuators. And so, technically speaking, you have to come up with a power supply for the tracker, and that might just be running an additional AC circuit in that trench, but it's not going to be thick gauge wire. It's just going to be for a control circuit for the actuator, so that's not going to be that costly. Then you have to buy the control system for about $200, and you have to buy the actuator for about $600. And then you have to buy those pillow blocks to put on top of each rail. And those are really the only additional costs necessary to go with a single axis tracking array rather than a fixed in place. And so spending $2,000 more to get that extra production in the wintertime, and you can use PV Watts, that modeling software we looked at yesterday, to show the increased production in the winter from tracking or the additional morning and evening production. But the short of it is, for a residential ground mount system, you're looking at about $2,000 in parts and really kind of insubstantial labor. In fact, the utility scale design is in some sense it's easier to build than a scaffold system where the modules are twice as tall. Because once they get twice as tall like that, you got to get up on a ladder, you got to move your ladder. Whereas this stuff is all done at waist height, so it's quite easy. So that's where we're kind of kicking up our design game in Mississippi on our next ground mount projects, is moving towards tracking arrays. And really the only problem is that we have to come up with a design ourselves and not, get it as a third-party vendor solution. And so there's a little bit of development work put into it. There's nothing to say that you have to have an actuator and a power supply and a control system. At bare minimum, just going with pillow blocks and having it be manually adjustable would be a pretty cheap way to get additional power out of your array. It would be a lot cheaper than just willy-nilly adding more solar modules onto it. And it'll give you that extra production in the season that you actually need it. So I'm actually a big fan of residential tracking. And, the downside of residential tracking is, there's more parts that could go wrong. What if the array gets stuck in a position? Well, that's when I go back to the late Mitch Hedberg. He was talking about escalators. And he says, I like escalators because the escalator, when it breaks, it just becomes stairs. It's like, oh, sorry for the convenience, stairs. It's the same thing. A tracking array, if there ever were a problem, it's not like it's not going to produce zero electricity. It'll just produce a little bit less electricity until you diagnose the problem and get it working again. And so when you look at your budget, and this is even like going with JR pricing, where I'm going deep into the bargain bin for solar modules, you look at the cost of the modules and being very stingy with the budget for just the DC side of the labor, just the charge controller, all the power still has to go through the inverter, and your racking system. What you're looking at is just, if you look at the fixed in place ground mount cost compared to when you're looking at like a 15 kilowatt system size, compared to adding $2,000 in parts to make it a tracking array, you're going to end up increasing your project budget by about 11% or so in order to gain 15 to 20% of additional production. And furthermore, that production is going to occur at times when you need it, not at times when you don't need it, like high noon, which is what you would get if you just added more solar modules to the design. And so what we can see is single axis tracking has really kind of taken over the solar market for utility scale. I mean, you still get some fixed in place, but most of the new utility scale solar projects are tracking arrays. The only reason why we don't see it at the commercial level is it's not being serviced. All right, moving on into generators. We have to go a little bit faster through these sections, so I apologize to the guy from Cummins who's here. But this is interesting. When I designed my off-grid home and I started picking out the generators for it, I went to the Generac website and they had a generator designed for off-grid renewable power systems. Well, that couldn't be any easier. That's the generator I want. It's designed to go for off-grid power systems. Turns out that wasn't the right choice. Buying the renewable generator was unnecessary. What does that mean? Well, first off, your renewable generator lines have control systems built into them, but your battery inverters also have control systems built into them that do the same thing in terms of turning the generator on when the battery bank drops. And so you end up getting two auto start functions, and that can actually get confusing. You know, if will the auto start function of the battery inverter actually start the generator that's renewable if we don't trigger the auto start on the renewable generator? You know, the renewable generator, you know, some of the features that were listed, like a larger oil pan so you don't need to maintain the generator as often. Okay, I mean, that's a nice feature, but is it a feature that's specific to renewables? No, that's more like you pay more money to do less maintenance. That's applicable to anything. You know, another part was the resonator. You know, so the renewable generator is less noisy than the non-renewable generator. Well, okay, you know, that's a good function. Customers like their peace and quiet, but I think that would be a function you'd want on any generator and not just a renewable generator. So you spend a little bit more for a little bit better quality of life, except aren't we really not running our generator that often? And so the noise level of the generator, does that really matter? You know, it turns out these renewable generators or off-grid generators are really designed to be used in a situation where they're being used frequently, as if you did not have the battery capacity or the solar capacity to meet the vast majority of your power needs, but then you needed to turn on the generator every single day or most days or every 3 days, you know, where you're relying on that generator. So if I was doing not a giant battery bank, but a small little starter battery bank that would be more reliant on a generator, that's when the renewable generator additional features could come in handy. You know, poking around the generator manufacturer website, one thing that was apparent was that the renewable generator produced a higher quality power than the non-renewable generator, you know, more expensive components. It turns out that that home backup generator is not really intended to run your home and all the electronics in your home 24/7, 365 days a year. If you're actually going to run your home off a generator 365 days a year, 24/7, then you would want to buy a more expensive generator with a higher quality output. Except in our off grid system, we're not running our generator that way. And furthermore, generators are pretty expensive to run. So here's our generator spec sheet. And it tells you how much natural gas or how much propane it uses over what rated load. And so let's say I had a 25 kilowatt generator running at 25% of the load all day. Looking at the price of natural gas or the price of propane, coming back to the cost per kilowatt hour of electricity, well, heck, that's pretty expensive. It's going to cost me a lot of money to get electricity out of my generator. And gasoline is even more expensive. And so what that tells me is I really want to do a system that's designed to not really need the generator except for a couple of days a year rather than a couple of days a month. And so if I'm designing my array to be large enough, my battery bank to be large enough, I'm not using my generator for anything more than to charge up the batteries. For that matter, the power quality is coming out of my battery inverter. It's not necessarily coming out of my generator as far as my home electronics go. And so I'm already getting some better power quality out of my battery inverter products than out of my standard generator. And last but not least, one problem we got into with variable speed generators is they really just want to throttle up to power the load. And so if you're trying to use the generator to overcharge your batteries during a maintenance process, you got to toggle a lot of different settings to turn a variable speed generator up to full throttle for charging your battery bank all the way up to the top. And so when it got down to it, it would have been better for us to just use a plain old dumb generator that we only fire up a couple of days a year to recharge the battery bank. We didn't need all the extra bells and whistles of a generator that came with higher power quality, less noise, and a variable speed output and its own auto start control system. We didn't need all that. So just a regular house backup generator, not necessarily the renewable line, not necessarily the high-end efficient generator, just a basic generator is all you need. And that depends on the size of your battery bank. But just remember, we're not running the generator every day or even every cloudy day. It's only when we go through a series of cloudy weathers, 1 day, 2 days, that third day of cloudy weather is when we're cranking the generator. And then it's going all the way back up to the top, and then the sun has come back out. So if we crank the generator at this point and get it all back up to the top, and then we go through 1 or 2 more days of cloudy weather, well, then it's sunny again. And so we're not, we crank the generator maybe at that point, and then we're back up to the top. And even though it's still dragging down a little bit, we've cranked the generator and reset our starting point. And so here we're looking at the difference between a 90 kilowatt hour battery bank and a 120 kilowatt hour battery bank and trying to determine when we're going to crank that generator. And so we crank it right here, we would charge it all the way back up to the top. Well, then it would drop all the way back down again. So on day 1, we crank the generator. On day 3, we crank the generator. And then if this is the starting point, we're back up here at the top in sunny weather. So we're cranking the generator once, twice, maybe a third time, maybe a fourth time, fifth time, sixth time, seventh time, eighth time, ninth time, 10th time. So if we have this 90 kilowatt hour battery bank in the period between November through December, we're cranking the generator 10 times, and let's just say that that's at full capacity for a few hours. It's costly, but we know our cost. Furthermore, the customer could be cutting back on their energy use during that time to avoid using the generator, to reduce the generator runtime. The guy who brought me into the industry now does tiny houses, and we're kind of like completely opposite in design philosophy, because he does tiny houses with incredibly small solar arrays and incredibly small battery banks. And he says, it's amazing what customers will get away with small systems, because they really get into actively managing their energy use. Whereas my philosophy is, I'm not interested in tiny homes. I'm trying to do full house size houses, and I'm trying to make it stress-free and worry-free with really very little energy management required from the customer. And so I would look at this and say, okay, well, what if instead of doing a 90 kilowatt hour battery bank, represented by something that is yay big, what if I did a 120 kilowatt hour battery bank and had just a little bit more range out of my system compared to 90 kilowatt hours? So I have 30% more because I go with a 30% larger battery bank. Well, in this exact same weather pattern, I would only need to crank the generator once, twice, 3 times, 4 times instead of 10 times. And so there's definitely a sweet spot in your model that you can hone in on with your battery bank size to reduce the amount of reliance that you need on the generator. And so based off the cost of gas and based off your hourly electrical load, you can calculate your generator runtime, the cost of running that generator versus the cost of buying new batteries, and just do a large enough battery bank to avoid that. And for a true home, not a tiny house, not a weekend getaway, but a true home, you get into needing either a 90 kilowatt hour or a 120 kilowatt hour battery bank. And with lithium ion at $500 a kilowatt hour at 120 kilowatt hours, you're talking about spending $80,000 on the batteries alone. Whereas if you use industrial flooded lead acid, you're in the $20,000 range. Some other things to think about with generator selection: a larger generator, a 20 kilowatt generator, will take 50% less time to recharge the battery than a 10 kilowatt generator. It might be a little bit noisier than a 10 kilowatt, but the runtime is less. And usually it's that the customer doesn't want to hear it. And so going with a noisier solution that only runs half the time might be the better option. So a larger generator is generally better than a smaller one. If you went with like a 5 kilowatt generator instead of a 20 kilowatt generator, it's going to have to run 4 times as long for the same all day charging capacity. Really, not a big issue, a small issue. You don't want to neglect the cost of gas when designing a battery bank, because what we can see is that it's very expensive to generate electricity with gas generators. We generally leave that for the utility scale guys to get the cost down on that. We don't have much more time. I want to get to smart home stuff. So the single line diagrams, I just kind of included for you to review so you can kind of see how some of these systems are wired up together. I put into the chat room an invite to my Slack community. If you haven't used Slack, it's very fun. It's a good way to do messaging, and that's where I put all my course recordings as well. And so if you want access to the course recordings, feel free to join that Slack group or just send me an email after class. And why don't I go ahead and put my email address in case any of y'all have to jump out right at the end, but still trying to wrap up in the next few minutes. So we cover string sizing and one-line diagrams in other classes. So I do have videos on how to go through this generation process. But what I recommend doing is going to the software that I use to generate my one-line diagrams is called Solar Design Tool, and they have a free trial of their products. But all of this stuff is after you get into the array area and you do your array layout. After you have to know some electrical knowledge to answer all the questions, but the end result is that all of the one-line diagrams are, well, I don't know if I can extract it the name of the time, but basically software now is generating these one-line diagrams on their own. And then you can download it the problem is a lot of the design software will not do the battery one-line diagram. So what I have to do is I have to do a battery-less one-line diagram and then export it into DraftSight or CAD and finish it out in my CAD software. Let's just spend a couple minutes on home automation. I have yet to sell a customer on a home automation package, although I think it's critical for off-grid. But the problem is there aren't very good home automation packages on the market. The closest you can get, I think a lot of home automation software is focused on like turning the lights in your room a different color, and they're not really focused on what it takes to be energy efficient. There are some functions built into battery inverters to help you with energy management. So you do have auxiliary circuits and trigger levels that will fire up circuits when the battery is at a low state of charge, such as a generator auto start, or that will shed service panels when the battery is at a certain state of charge, or oppositely, that will turn on circuits when the battery's at a full state of charge. So I don't think it's a bad idea to use like a auxiliary output and trigger a feature in the home like a water fountain out in the yard, so that when the water fountain is bubbling, that means your batteries are at a full state of charge and your home has healthy battery life. So it's not a bad idea to have kind of a combination of auxiliary loads to kind of trigger to the customer, and coach them on when they have a full battery level or not. Triggering auxiliary heating. This is a thermostat, and the thermostats have auxiliary heat triggers in them so that if you're on gas heat, it could turn on an electric heater. Well, you can use the same function to turn on an electric heater when your batteries are at a full state of charge, if only you could get your thermostat and your solar array to talk to each other. So sometimes you can get that as a function in your battery inverter, but let's think larger. What if it wasn't just one circuit? What if we wanted to have tons of circuits and tons of triggers? What would you do? So this is one of my favorite thermostats, and this is old school thermostat controls. I don't really have time to get into it, but what I really wanted to point out is that they have, this auxiliary heater function. And so where like energy management with home automation is you're going to have to create your own home automation system, like smart things, all the consumer oriented home automation stuff out there is not focused on energy efficiency. Even like Nest, like that smart thermostat, doesn't have the minute by minute level of controls that you really want, because your electric use varies minute by minute. So like Nest can you can program with smart things your Nest thermostat to talk to your electric service panel, but it'll only dial back your thermostat like every hour, not every 15 minutes, or every 5 minutes would even be better. So there's a home automation platform called Home Assistant, and that's designed for a computer that's a $40 computer called Raspberry Pi. So if you've heard of Raspberry Pi, but you've never gotten into it, this is a nice project for you that's kind of low budget. So let's talk about some of the home automation platforms. One of the most important things about home automation, and we're going to wrap up pretty quick because I know we're at the end of our time, but there's a platform called Z-Wave. So Z-Wave is, if you remember landline telephones, and then you remember when landline telephones went wireless, and then you remember when landline telephones went wireless, but you could walk more than 20 feet away from your phone and still use it. Z-Wave is the wireless landline telephone that you can walk more than 20 feet away. It's that communication protocol. It's a little bit better signal than remote controlled, but it's much less energy intense than Wi-Fi. You can go on Twitter and research Nest thermostat, and what some Nest thermostat users don't realize is that there's a power circuit for thermostats, but other thermostats can run off of batteries, and the Nest can run off of batteries, but it can also run off this power circuit. And so if you take a thermostat that is a battery-only thermostat and you swap it out with a Nest, and you try to run your Wi-Fi touchscreen LCD on batteries, the Nest thermostat will drain your batteries in 2 weeks. It needs that, what's called a C-wire power input. This thermostat, it's made by a company called Radio Thermostat, is a Z-Wave thermostat with just a basic LED screen that is low energy consumption. And the Z-Wave platform, compared to Wi-Fi, is a low energy platform. And so you take a Raspberry Pi and you buy the Z-Wave transmitter, and then you can find Z-Wave all sorts of stuff. You can find a 40 amp switch that you could use to digitally turn your solar array on and off if your batteries were at a full state of charge, so that you didn't overcharge your batteries. You can get a Z-Wave breaker switch. This is a Z-Wave energy monitor. It costs about $80, and it just clamps around the main of your house so that you can determine when you're inflowing or outflowing. And then it's the Home Assistant platform where you have to do custom programming to say, okay, if I'm outflowing onto the grid, turn my thermostat up and crank the AC. But if I'm not outflowing onto the grid, turn my thermostat down and don't run the AC so hard. Likewise, you would, the hardware cost, Raspberry Pi is $40, the Z-Wave stick is $30, this energy monitor is $90. When you look at the cost of a manufacturer provided inverter monitoring system, it's like $300. So for the same hardware cost as your online inverter monitoring system, you could buy all the hardware you need for a custom automated home energy management system It's just that you have to program it yourself. This stuff is not quite ready for, a white box consumer product, but for a ambitious hobbyist, it's something that can be fun to look into. In fact, what I'm looking at is the Wi-Fi controllable outlets, like for the Samsung SmartThings platform. They cost like $40 each. They're terribly expensive. Whereas you can get remote control outlets, and these cost about $5 each. RC costs less than Wi-Fi. And so for my system, I've bought some RC transmitters and wired that up to my Raspberry Pi so that my Raspberry Pi computer can turn dedicated outlets in my house on and off as a function of my electric load, because I'm monitoring them through a Z-Wave energy monitor. So like all this stuff is coming to market. It's just not consumer grade yet, but it is possible for, let's say less than $500 of material costs for you to throw together a very sophisticated energy control system for your home. And that has huge advantages for, living off grid. I think that goes without saying. Putting your freezer on a timer, turning it on, only having your freezer run during the day and coast at night. It could also be where instead of having one refrigerator, you have 3 refrigerators. You have a small refrigerator for daily use where you're opening the door and shutting the door. And then you have a refrigerator for storage that you only run during the day and you let the thermal mass coast at night. Maybe you take 2 refrigerators and you fill in the back half of the fridge on each of them with jars of water for cheap thermal mass so that you don't lose all that cold when you open up the door, and have 2 fridges instead of 1 and just, do more with thermal mass. So that I want to get you out of thinking that living off grid is something where you're energy impoverished, to say, no, you can't have luxurious living. You can have a hot tub. You can have a water fountain. You can have multiple refrigerators. You just have to have some intelligence. And that intelligence is something you're going to have to hack together on your own. So we're almost done. I'm going to go through this section really quickly. But this is kind of where solar design goes for retrofitting. I can't get into all the details. It's just not enough time in class. But this is where you get into moving beyond what the manufacturer says you can do with this stuff. So, what I've done is put kind of important spec sheet items into the slides. And if you have questions, you can ask them later. Some of this stuff we've mentioned in class. Like yesterday, we talked about resistive loads versus motor loads. But basically, what we have here is an everything array, where we have a flooded lead acid battery bank, we have a lithium-ion battery bank, we have a grid-tied lithium-ion battery inverter, and then what this would be is on an automatic transfer switch on a generator interlock. So that when the grid goes down, you flip it and you have your very cheap off-grid 120-240 battery inverter on its own battery bank that could then go and turn on your batteryless solar inverter, or in this case, it's a battery inverter. So you can program the Solar Edge inverter not to charge and discharge its battery for daily consumption, but instead to only turn on if your load goes above 40 amps. And so you could have a lithium-ion battery providing spiky loads and a lead-acid battery bank providing base load. And the only problem with this stuff is that it's not under warranty. then again, buying a $50,000 or $60,000 lithium ion battery bank compared to a $3,000 lithium ion battery and then a $18,000 flooded lead acid battery, that's a lot of cost savings compared to the warranty on just one system component. And so, I haven't found the right customer to do this yet, but it's, there's an argument to say, hey, we like Solar Edge. We like the DC optimizers for shade mitigation. We like the high voltage home run for ground mounts. The problem is Solar Edge says you can't use our stuff off grid. We like an automatic transfer switch for backup load for emergency medical equipment, but we also want to use the solar array off grid. We also want to use it during a power outage. And so this configuration kind of shows a shared DC bus, high voltage, feeding both a high voltage lithium ion battery bank and then a 600 volt charge controller that charges a 48 volt battery bank that's on a generator interlock switch that can be switched over during a power outage. In this way, your solar array remains grid tied and can backfeed the grid and sell back, but you could also switch around and just as easily use the exact same system in an off-grid setting. And so the rest of these slides kind of go through, hey, Solar Edge says you're not allowed to do this stuff. You're going to void the warranty. But then when you go and you read the spec sheets, what you realize is, hey, there's a minimum number of panels that you need to turn the system on. And there's a maximum number of panels that you can have before you're overpowering the inverter. And the range of power in between the minimum and the maximum, that is how much power you can draw off of the high voltage DC bus without disrupting the inverter protocol. And so you could, this is overcomplicating it. You could have just two separate solar arrays, fine. You could just do AC coupled, fine. But in this, what I call Franken solar is a way that you can get double redundancy. If this inverter fails, you still have that inverter. If this battery fails, you still have that battery. So you get double redundancy, but you're not repeating any parts. You're not double stacking inverters. You got the grid tie functionality, but also the transfer switch. And what's interesting about this kind of platform is it can be built in stages. You could do just the batteryless solar array first and have a generator for backup power. That's what most solar customers would have today. But then later, you could go and add a 48 volt battery bank on a generator interlock switch just to kind of hang out and provide you with battery backup power during a blackout. And then even later than that, you could go and say, well, I don't want to just charge my batteries with the grid. I want to charge them with my solar array. And so you tack on a 600 volt charge controller to this shared DC bus and use that to charge your 48 volt batteries. And so you don't need the grid. And then you could cut the grid out and switch your battery inverter over into a demand management profile and have your lead acid provide your base load and your lithium ion provide your peak loads or dynamic loads. So all of that stuff works. It's just not supported by the manufacturers who are really only focused on one particular application, whether it be off-grid products or grid-tied products. There's not really a comprehensive system. And so I've added material budgets that you can look at it. You can also go to my website where I have in my shop, So here's my website. If you go and you click the let's see, that doesn't look very good, does it? Let me let me try and reload that really quick. Um, there you go. So right here under on-site, what you'll see is pricing for a couple of different configurations for different size battery banks, inverter outputs that can just assist your budgetary information. And kind of on a final note, because I know we're over time, um, what I do with my systems here in Mississippi is I put them all on a whole house transfer switch. And so we disconnect the home from the grid during the day. And then if they don't want to give up their grid connection, we reconnect them through the transfer switch at night. And so we keep the battery and the solar array completely isolated from the grid. And then we reconnect them to the grid when the system is not quite good enough. And that way, you don't need the 120 kilowatt hours. You can get away with something that's much smaller because they're not yet leaving the grid. But the difference between, and this is called grid assist, the difference between a grid assist configuration and what we're doing now with grid tied batteries is a grid assist configuration takes you completely off the grid with inverters that are high amperage output to power your whole house rather than something that's like what Solar Edge has to offer, which is low amperage output to power critical loads. And so we're kind of do just this portion of the system for now with solar. Take the home off during the day, reconnect at night, and that way we don't have to deal with any interconnection at all. And it trains the customer so that once they're ready to go completely off grid, they can. But otherwise, they can see what it's like to be off grid without overspending, without oversizing the array, without oversizing the battery bank. You could do something quite smaller that is, I think, more in line with what customer wants and needs are with solar than what the batteryless systems have to offer in today's market.